So what we're going to do today is we're going to start from scratch. We're going to design our own circuit board. We're not going to do anything more complicated like creating custom parts. So the great thing about KiCad is that even though it installs to about 6 gigs, it has a massive parts library. So pretty much anything you're going to need, it will have. Hey John, the projector just turned off. And that's one of the beautiful things about KiCad is if you have ever worked with Eagle, you will know that it doesn't come with a very good stock parts library. So it's nice not to have to uh, go into a project and design every single part for that project. You can just kind of, it's a little bit like Lego in that way. Once you know how things go together, you follow the guidelines in the data sheet for that chip. There will be some customizations for the project that you want to do, but the project that we're going to do today is basically going to be ripped right out of the data sheet, so we don't have to worry about any potential weirdness. It's a technical term, weirdness. So what we're going to do is we're going to design our own USB to UART with a USB-C connector. And KiCad is going to make that extremely easy for us. Yes, Bash. So if you've heard of Serial, RS-232, RS-232 is a spec on top of a universal asynchronous receiver transmitter, or a UART. RS-232, it basically stipulates that the control signals for those have to be plus minus 15 volts, or at least plus minus 10 volts. So if you've ever worked with Serial, like if you've ever tried to get into a router, or you've tried to communicate with a managed switch with one of the special Ethernet cables with the DB9 on the end, it's Serial. It's a UART. That's just what it's called. Correct. Yeah. So this is a device that it's going to give us a communications port, and it'll allow us to communicate with other serial devices at the voltage specification that we pick. And in this case, it'll just be 3.3 volts to keep things simple. Some more complicated devices have a way of setting the output voltage, but the chip that we're going to use today, I don't think it's complicated enough to do that. So correct. So well, this chip, it's set up that it will do several different output voltages. It has a pin called I believe it's either VIO or VCCIO, something like that, that allows you to set the IO voltage from an external voltage regulator. So what we're just going to do is we're going to take the 5 volts in from the USB port, crank that down to 3.3, and just power everything with it. It's a very simple design, but effective. Another way to do it is there's general purpose I/O pins on this chip that you could potentially use to power up and power down I/O regulators. So if you wanted to switch in a 1.8 volt regulator, because it's pretty common for high-speed devices like your Switch, for your Nintendo Switch, for example, will use a 1.8 volt UART, and 1.8 volt UART boards are very uncommon. But we're not gonna do that today. So the first thing we're going to do, since we've decided that we are going to use this specific chip, which is the FT232R, or the RL specifically, this chip is specifically designed for this purpose. It talks USB 2, creates a COM port. It works both on Windows, Linux, and on OS X, OS 10, whatever it is. It has drivers for all the platforms, and its purpose in life is to talk serial over USB. So it's going to be very simple. There's a few things that we're going to have to take care of. but it shouldn't be too bad. So if we kind of take a cursory glance through the data sheet here, we can see some of the things that I've mentioned, like RS-232, RS-485, kind of voltage configurable I/O. We are going to need to do an external oscillator, but as you'll see later, FTDI do a really good job of giving you example schematics that you can, kind of springboard your design from. And in this case, we'll basically be completely copying, but that's what they're there for. So what we're going to do is we're going to be using a USB-C port to control this whole thing. So you can see in the data sheet here, it's got drivers for, Android, literally everything. So this is kind of a block diagram here that breaks down exactly how this chip works. So we have the USB pins, which are important. It has an internal 3.3 volt regulator, which we're going to use for this purpose. It simplifies the design. It lowers the cost of the bill of materials, which is important for electronics, because if you're selling 3 million units, 3 cents on 3 million adds up pretty quick. Although it'll be more than 3 cents, but you get the point. We have our oscillator pins, which are technically optional, but having worked with this chip before, I can tell you that you really do want an external oscillator because the internal one is not very good. It drifts. The precision is not quite right, so you'll start getting framing errors on your USB packets, and you don't really want, if you're dumping, say, a binary out of a managed switch because you want to reverse it, you don't want a random bit flip half a megabyte into that potentially gig-sized binary. So you want this thing to be as stable as possible. And then on the other side here, you have all of our, the UART control with programmable signal inversion. That we're really only going to be dealing with 2 signals right now, mainly transmit, receive, but the UART and the serial spec contain other pins like ready to send, due to send. There's I think there's 9 or 10 pins in total in the full serial spec, but they're pretty rarely used, and unless you're doing something like proper RS-232, you can pretty much ignore them. I mean, if you go to Amazon and you look at any of the USB to UART boards, you'll basically only see power, ground, and transmit and receive. So that's really all we care about. We could break these signals out, but for the purposes of this project, we're not really going to worry about it. We're going to read the data sheet and see what it specifies. But in general, the FTDI chips are designed so that these signals can just be left to float. In like a high signal integrity situation, or if you're going to be driving this thing at the full 3 megabit baud rate, you could potentially have crosstalk from transmit and receive that would affect these other signals and change the way that the chip actually works. But for our purposes, we're probably only talking a maximum of 115K, which is not much. So this will give us the full pin out of this chip, and I'm not really going to go over it at this point. We're going to kind of go through pin by pin once we actually get into it. What I really want to get into is the example schematics that they have listed. And I'm not sure how far into this data sheet it is. So here's a first example, which basically powers the entire system off 5 volts. So what that would result in is our transmit and receive would be 5 volt out. And what we really want is 3.3 volts. So basically what you see here is over here, USB port, you have your power coming in. Optionally, they're including a ferrite bead here, which is essentially going to form a low-pass filter with the input capacitor. And what that means is This will block high frequency noise coming in from the PC, but also block any noise generated by our board into the PC. It's kind of a nice thing to have, but for the purposes of the project, we're going to omit it. But basically, you see, we have our chip, we have some decoupling on the 3.3 regulator, even though we're not using it. The data sheet still, the internal regulator is going to be running always, so it needs to be decoupled, or you'll cause problems. Because it's a linear regulator on the inside, it has to have decoupling, or the output will swing wide. It can do different things that could damage the chip. It could alter the operation of the chip. But in general, decoupling is going to be necessary on all of your power lines. So this is another 5-volt option, and the difference between this one here is the voltage divider here we have with these resistors, and that basically you would do that in the case that you have a self-powered board where USB won't be plugged in. So you could potentially be backwards powering the chip through its IOs, which would cause damage. And there's a couple of other setups here that we're not really going to worry about, like selectable supplies. Let's see if they have a 3.3 volt version. It doesn't look like they do. So basically, what we're going to do looks a lot like this schematic. Here you can see, if I zoom in a little bit, this VCC IO pin. That's going to determine the voltage that this FT232 tries to communicate with. That's the pin that we could set to various logic levels that would control our output. In this case, instead of tying that to VCC, which will be powered at 5 volts, we're going to tie it to the output of the 3.3 volt regulator. Because it all depends on the purpose of the board. 5 volt used to be really common. Now 3.3 volt dominates most things. Like all your Arduinos will be 5 volts, but newer Arduinos, like the Due, some of the more powerful boards, are going to be 3.3. And even more powerful, like I said earlier, like your Nintendo Switch, that's going to be 1.8 volts. So in general, the higher the speed of the CPU, the lower the voltage is going to be. And the reason for that is because the higher your clock speed, the more power you draw. The lower your voltage, the lower the power you draw. So it kind of evens out the higher current consumption of faster clock speed of the lower voltage. It makes things more stable. You have less power flowing through the chip. So it's like a PC processor won't go above about 4 gigahertz without being like cooled with liquid helium. The higher your power, the more unstable things are. I mean, we're not really going to be getting into anything like that today, but in general, that's how it works. Is the more the more power, the lower the voltage. Right. But most commonly, your projects that you find today that are anything above an Arduino, like a Teensy or any of the FPGA boards, it's all going to be pretty much 3.3 volts. So that's what we're going to target today is 3.3, just because it's common. I believe all the IOs in the Pi are 3.3. Yeah. So I think there are some 1.8 volts, but So this is basically what our our schematic is going to look like. There'll be a couple differences, like this is probably a USB-A connector or maybe a USB-B connector, but we're going to go for USB-C because that's the new hotness. So what I'm going to do is I'm just going to open up KiCad and hope it hasn't exploded. So I'm going to create a new project. I'm just going to call it intro because reasons. So when you first open KiCad and you start a new project, you're going to get a series of buttons here. And so each one of these buttons is either a different editor or a calculator of some sort. I'll explain what each one does. So the first one here, if you highlight over it, it's going to tell you that it's your schematic layout editor. That's where we logically position all of our parts. It's where we make all of our connections that aren't necessarily electrical connections. The schematic is like it's the drawing of how things work logically, not physically. And then to the right of that, we have the symbol editor, which is, so in your schematic, you place symbols, and you place text, and you place wires. They aren't real wires, they're the connections of your board. It's where you tell the circuit board where all the connections are, basically. And the symbol editor lets us, so if I open the symbol editor, it's going to load all of the symbols up. And let's say I want like a 7400 series. That's an example symbol. It's a NOR gate. Not really important, but you can see it has pins, it has a body, it has a name, and it has that U. That U is our reference designator, which means that it gives a part a name, basically. If we know something is U1, we know that U1 is U1. So, like ICs, chips, are called U for reasons, historical reasons. Resistors are R, capacitors are C, diodes are D, and basically everything has its own class of reference designators. S would be switch. M, I'm not sure about that. I don't know about that one either. I'm sure it maps to something. I just don't know it off the top of my head. To the right of that, we have the PCB layout editor, which is where kind of where everything we're going to be doing tonight will be happening there. I mean, we're going to be doing some schematic stuff, but what we're really here for is the circuit board. This is where we take the physical representation of our symbols, which are the actual chips, and put them in place. And similar to the symbol editor, we have a footprint editor. So if I just fire that up real quick, and I open up, let's say, capacitor, we can see there's a capacitor drawn on the screen. We have the red here. So if we look at the colors over here to the right, you have FCU, which is front copper, bottom copper, a whole bunch of layers that we don't need or care about at this moment, like the adhesive layer, the paste layer. We have the silkscreen layer, which is where your text is actually silkscreened onto the board. So everything that's blue that is turning off and hiding here, that's going to be drawn on the board. Where it says ref star star, that's KiCad's kind of built-in internal, this is where the reference designator goes. So if we have U1, once we've put it on the board, that will render as U1. It just tells us in the editor, logically, that's where this text will go. And then we have like a fab notes layer. That is only visible to us in the editor. So when the boards are actually fabricated, unless you've explicitly set, I want to include the fab notes on my silk screen, that's not going to get printed on your board. The other important layer that we need to note is the courtyard layer. If it would, yeah. So if you see the white box, that sort of bounding box that's around our component, we see it turning off and on. Basically, you draw a courtyard around a component so that if you have two components that their courtyard is intersecting, you get an error. I mean, sometimes you want to overlap two parts, like if you've ever seen like an RF board that has dual antennas and you move a 50 ohm link to change the antenna, they usually, for reasons, overlap one of the pads so that you have three pads for two logical components. And that would technically be an accepted error, right? So that gives us kind of an overview of the layers. I mean, there's more like edge cuts and margin that we'll kind of get into once we're actually drawing the board. But those are the relevant layers that we're dealing with. Is mostly copper, silkscreen. If you're getting your boards assembled, it's paste, but it's kind of outside the scope. Mask. So the solder mask, where this purple is drawn here on the screen, is where you'll have an opening in the colored solder mask on your board. So if you say if you have a circuit board that's green, that green coloring is called the solder mask, and that's a mask that's applied that will block solder. Solder will not adhere down. I mean, you might get like a ball that sticks, but it's designed so that you have solder mask between your pins so you don't get a bunch of bridges. So what this does is, this says I want a hole in the solder mask over my pad so that the pad is exposed so I can solder to it. It's another important layer. It's not one we have to really think about now, but it's there. And of course, for every layer, pretty much you have one duplicated for the front and the back. We're only dealing with a 2-layer board today, but if we had a multi-layer board, there will be more copper layers out of the scope.
So 2-layer, that means the mask layer and the copper layer?
No, it's 2 copper layers. So you have a copper layer on the front and a copper layer on the back, and then you have a separate front and back mask, solder mask, silk screen layer for both sides.
Okay, so 1 layer is one-sided, 2 layers two-sided.
Correct.
Other layers have sandwich.
Yeah, and then another common one is 4-layer. So you would have your 2 outside layers with your mask and your silk screen, and then 2 internal copper layers. And then the stack up of that layer, what it's called, is the distance between the layers inside the board. So if you were doing an RF board that needed a very specific impedance, which is another term that's kind of out of the scope of this, but in order to get a specific impedance, you have to have the layers a specific distance away. That will tell you how wide you need your tracks. There's calculations and numbers, but basically, you tell the board house, I need this stack up, or they say, this is our default stack up, design your board to that spec. So now that we've kind of taken a look at, let's see if I can, no, we'll wait on that. I was going to see if I could show you the 3D model for that, but I don't think you can view that from the footprint editor. So what we're going to do is we're going to just jump into the symbol editor, not symbol editor, the layout editor, and we're going to start dropping some symbols in. So you should get a screen that looks like this. So what we're going to do, the button to add a symbol is over here near the top right. It looks like the same symbol editor button to say place a symbol. So we're going to click that. And then you get the little pencil that tells you that you're in an edit mode, and you just kind of click inside. It's going to load up all of KiCad's parts, and there are quite a lot. So what I'm going to do is I'm just going to type in USB-C, and there are a couple traps in here. So if we look at this connector, this USB-C connector, there's actually a problem with this specific connector, if you see, I'm not really going to go into it, but if you pay attention to this one, there's one D minus and one D plus. But if we look at this one, there's two. And so the way that USB-C is reversible is that it has two pairs of each, and they have to be connected together. So if we were to use this plug, it wouldn't be reversible. Your USB-C cable would work one direction, but not the other direction. It's kind of a major oversight. So what we're gonna do is so with USB-C typed in up here, we're gonna pick USB-C receptacle 2.0, not USB-C plug 2.0. So we're gonna place that, and then while we're still in this, we're gonna look for our FT232RL. I'm really glad they have this part because I didn't check before I started this today. And that would have sucked. So let's go ahead and zoom in, and we're going to kind of inspect the parts, the pins that we have here. So on the side here, we have our transmit, which is transmit out, out of this device. So if you've worked with serial before, you would know that you need to connect the transmit out into the receive in of your target device. We want to remember that when we're doing the silk screen on this board. But anyways, so you can see transmit here, receive, and then we have all these other signals. A lot of times, some of these boards will use the RTS signal to do like a reset. So the early Arduinos, before they switched over to a microcontroller to do the USB to UART, they use this FT232RL, and actually a lot of the Arduino clones use this chip, and that's what they do. Is that I believe it's the RTS pin. It's the ready to send. What the software will do is really quickly open and close the COM port, and that will cause a transition on one of these pins that would reset the chip, send it into the bootloader, get it ready to receive software. But you can see these C-bus pins down here. If we were to look at the data sheet, it would show us that these are general purpose outputs that we could control through the FTDI driver. Like I was saying before, if we wanted to have like a software selectable output voltage, we could use these general purpose IOs to drive either an intelligent switching regulator that could, add an input, set its output voltage, or just switch multiple voltage regulators. We have our USB D plus, D minus. We have our oscillator reset, a bunch of grounds, the VCCIO pin that's important to us, our 3.3 volt regulator output pin, and a test pin, which if you look in the data sheet for that, it will say to leave it unconnected. It's kind of a factory thing that it's undocumented, and if you connect it to anything, you could potentially damage the chip, is what the data sheet says if you were to read it. To keep this short, I'm not actually going to go through, but I implore you, if you want to get into electronics, to go around and start reading your data sheets, because that's how you get into it. That's how you learn. That's how it's boring, but after a while it becomes like, why did they do this? How did they do this? Why did they implement it this way? And you know what the best part is, honestly? Finding mistakes and errors and issues in a specific implementation. And you can go in your head, they screwed up. And then you email their dev team, and then they get mad at you. That's like half of electrical engineering. So if we go back to, let's see. If we go back to our schematic here, we'll see that we have a VCC connection. We also have the USB D plus and D minus connection. So let's just start with that for now. So if we open this back up, and the tool to route wires is this green wire over here. It says place wire. So what we're going to do is we're going to connect the two D- pins together. Otherwise, your connector will not be reversible, and it will work one way. The lag on the screen is really bad. So there we go. So now that we have those two tied together, we're going to tie the FTDI. So this is going to be really ugly because it has the two pins flipped, but I'll line it up right. Now, this design isn't going to have a lot in the way of protection. So there's things that we could put on the USB traces, like current limiting resistors, transient voltage suppression diodes. So if you have like a static shock to the device itself, the transient voltage suppression diode would be able to suppress that that high voltage spike. Not necessarily sacrificing itself because it is such a small spike, but that's what it's designed for, is to sacrifice itself instead of the device. The other thing we could do is include a ferrite bead on the USB voltage input. The other thing we could do is a resettable fuse. It's things we're not really going to do. So let's go to the data sheet and look at the decoupling capacitors that they're using. So we can see that VCC is coming in, and they don't really label it very well, but if this were a USB-A, pin 1 is the 5-volt pin on the USB connector. They have VCC, and tied to VCC over here, they have 100 nanofarad and a 4.7 microfarad capacitor decoupling to this chip. So what we're going to do is we're going to wire VCC with these decoupling capacitors. So let's go back to our place part. And all we're going to do is we're going to type in C. And it's going to give us this device C, which is, I don't know if it's built into KiCad or if it's just like one of the logical first symbols that you're going to add, but that's all we need for capacitors. Later we'll assign a footprint. So let's just put a couple of these in here. So what we have to do is we have to set the value. So if you look, there's C question mark, which is, if you look on all the parts right now, we have J question mark and U question mark. KiCad by default does not assign our reference designators. You actually you have to go through and do that manually. And when I say manually, you open a dialog and hit a button. But so the reference designator is the C question mark, and the value is C. If we were to right click and go properties, edit properties, or if you have mouse over it, just hit E. There's one thing that you'll learn about circuit board CAD tools. It's that keyboard shortcuts are the way to go. So once I show you a keyboard shortcut, I'm going to start using it. And if you get a little bit lost, just flag me down and I'll backtrack and we'll go over it. So if we look here, reference is, like I said before, C question mark, value is C. So if we remember from the data sheet, there's 100 nanofarad. So I'm just going to type in 100 nanofarad. And that's really mostly for documentation purposes, so will we know what's going to be on our bill of materials, what's going to be in the schematic so we can read it. It's mostly for the humans. Like KiCad does not care what this value is. KiCad can do some simulation, but I've never done it before and we won't be doing it today. So once we've got that set to 100 nanofarad, it will update on the display. But the other thing we can do is if you mouse over this part and you just hit the V key, V, as in variable, it will open up the edit value field, and you can just, you can toggle the visibility, the text orientation, make it bold, whatever you want to do. So if we right click this again, and there's duplicate here, which is the C key, you'll see we get a copy, and then I'm going to edit the value again. And if I remember correctly, it's 4.7 microfarad. Yep. So now that we have our capacitors, the next thing we're going to do is we're going to add some ground points. So up here in the top right, there's this place power port, which allows us to add special symbols to KiCad, which is our ground symbols, our voltage symbols, things that aren't really parts but logically need to be part of a schematic. So what I'm just going to do is I'm going to search for ground, or just GND. This is the symbol that KiCad likes. And what you can do, I could put this down over here and then run a wire to it. But the other thing I can do is if you look at the circles that are on all of these pins, KiCad displays that to you and says, I'm unconnected. I need to be connected. So what we can do is we'll just drop this ground right on that, and you see how that circle disappeared. And now that we've placed it, if we click again, KiCad's going to open that menu and say, what power symbol do you want to place? So to be quicker about it, you can hit the escape key, you get your cursor back, go over the other ground, hit C to copy, and it's just, the workflow is a little bit faster when you do that way. Lots of little trivial things you're going to get annoyed about doing this. So that's one of them. So what we're going to do, if we were to, let's see, place a wire, we can see that the shortcut for that is Shift W. I don't really know who did their shortcuts, but now if you do Shift W just out in the middle of nowhere, it's going to try. Oh, well. See, that's funny because it says Shift W, but it's actually W. Well, welcome to open source. Anyways, if you hit W out in the middle of nowhere, it's going to try and draw that wire for you. So what I like to do is you just get over where you want to start it, and you just hit the button. That's another thing about KiCad, is that you're going to run into a lot of like user experience things where you go, why did they do it this way? And then you remember that the entire thing is maintained by people and not companies, and people are human and aren't getting paid to do this. So it has some issues, but not nearly as many as it used to have. And then I'm just going to move this out of the way so that that wire isn't running directly through the center of it. So what we've connected is the 5 volts output from the USB connector into the FT232. So if we go back to our schematic, what we've drawn is this trace right here, and we need to connect our capacitors. Because we're ignoring the ferrite bead, the low pass filter that ferrite bead creates, we're also going to ignore this 10 nanofarad capacitor, because that's really only useful in conjunction with the ferrite bead. The two components are what creates the filter, so we're just going to kind of ignore them. So the next thing we need to do is we need to connect up the two capacitors that we've drawn. We've already connected the ground. And just the way that they've drawn it here, you could draw it that way, do one ground symbol, but the way that I like to draw it is one ground per part. And then I'm going to violate that rule in about 5 minutes. So now we're back here. I'm going to scroll in, and I'm just going to draw in the connection for our two capacitors. So this device is now, it has its decoupling capacitors. The next thing that we're going to look at is the 3.3 volt regulator output. Now if we look, in this drawing, it only has the decoupling capacitor, but we're going to make another change in that this VCCIO pin, instead of connecting to 5 volts, will connect to our 3.3 volt out. So let's go ahead and do that. So I am just going to take and copy this capacitor, and then I am going to scroll in a little bit, and then if I right click, let's see, if I, to get the mirror, or to get the text facing the right direction, I can never remember. Well, doesn't want to do it. Sometimes KiCad doesn't want to do it. So to move this, you could right click and move, or you could just hover over it and press M. No. Unfortunately not. So we're going to copy another ground for this. We are going to connect this to our 3.3 volt out, and then connect VCCIO to that. So what we've done is this VCC pin is internally connected to a regulator that's inside this chip. If this chip didn't have this feature, we'd have to bring our own, but it does, so we don't. And with this internal regulator, so on a normal voltage regulator, a linear regulator, you have 3 pins. You have a voltage input, a ground, and an output. The input is tied to this input here, and the ground is tied to one of these ground pins down here that we'll get to in a minute. So what we've done is we've tied that 3.3 volt out to the VCCIO, but one thing that we're also going to do, because we want the user of this board to be able to access that 3.3 volt rail, we're going to add another power symbol. Not. There we go. I'm going to type in 3.3 and then 3.3 volts, and then just attach that on there like that. So basically what these power symbols do is they give those wires, also sometimes called nets, you'll hear, even KiCad kind of blurs the nomenclature, but net or wire, it's the logical connection. It gives that net a name so that when you import it into the circuit board editor, it knows what track goes to where and how to track it logically. So if we were to look at the name of this net, it would say probably something like plus 3.3 volts. It's just the logical naming. Now, we could have put a label on there. If you go over here to the letter over the green line, place a net label. I'm pretty sure if we do that, yeah, that doesn't work. Never mind, I lied. I don't know if there's a way to edit. Anyways, behind the scenes, that's how these power symbols work, is it gives these things a name. Apparently there's no way to view that name in KiCad itself, but you get the point. So the next thing that we're going to look at is the 4 ground pins on this chip. And if we go to the data sheet, and it actually has us ground the test pin too. If we do control find for A ground, let's see what the pin description is. So all of our other ground pins are just regular grounds, but this A ground pin is for, so the way that this chip generates the 48 megahertz USB clock is with a multiplier, which we don't really need to care about. If we're in like a high fidelity situation and we needed this thing to be absolutely, bulletproof, we would potentially put a filter on this analog ground or isolate it on the board physically in such a way that it had greater noise immunity than our regular digital ground. Because you don't want noise on the clock for USB, because then you get back to frame errors, and it's the same sort of thing. But having a proper external clock will bulletproof it enough for us. If we also look for the test pin, we read it puts it into test mode, must be tied to ground. So just like the example schematic, we're going to tie that pin to ground. So let's go up here and we'll copy one of our ground symbols. And we'll attach all of our grounds and the test pin to ground. And believe it or not, we're almost done here. Let's also connect so a lot of these USB connectors from KiCad have both the shell of the connector and the actual logical ground pin broken out. This one, in this case, is called shield, which is actually going to be connected to the protective shield mesh on the USB cable itself. A lot of times what you'll find is a high voltage capacitor, like a 1 or 2 kilovolt rated, like 1000 picofarad capacitor, and a 1 megohm resistor. Those are there, again, for ESD sensitivity and dissipating that charge if it were to come backwards in over the shield. Again, we're going to omit these safety devices. So let's go back to the data sheet and take a look at the reset pin. So we can see that unlike the other symbols, or well, some of the other pins, there's a pound on here. And if we look at KiCad really quick, we'll see that there's actually an overbar on that pin name. So either the pound symbol or the overbar indicates to us that this pin it operates differently from other pins. And if we look, we read the description is active low. In digital signals, there are things that are active high and there's things that are active low. And what that means is, so the reset pin is it resets the FT232R. That is, it puts it in a power on state. All of its internal registers, everything. You maybe messed with a development board that has a reset button. It's a hardware event that it erases the slate essentially on that chip and puts it back into, as if it were fresh and brand new. We could put an external reset button if we were doing like an initial run of development and test boards for a production version, but again, it's not really necessary here. In this case, this chip has an internal pull resistor, and what that means is that because this is an active low, if we pull that signal to ground, if we tied it directly to ground, it would forever keep that chip in reset. That is, it would do nothing. While it's in reset, it's not communicating. It's like a while loop, like a while one loop that is doing nothing but constantly wiping the slate clean, resetting all the registers to whatever the power on reset is. As soon as you raise that reset button above a set voltage that's listed somewhere in the data sheet, the chip can start, it can do its thing, it can communicate, it'll recognize as a device in your operating system, it will work. A lot of times you'll find that, like it says here, pulled up to VCC. A lot of times, like with an Arduino, you'll see like a 10K ohm resistor pulling that reset pin up high. In this case, this chip has an internal resistor that's built into the die, so we don't have to do that. We don't have to worry about it. Again, if this were a high fidelity device where, it needed to be 1000% bulletproof, we would put a resistor on here because that's what you do. That's correct. Both ends. Yeah. And that's because if you had the strain relief on one end fail and the shield no longer connect to that end, then the shield is still connected to ground because you're transmitting ground through the core of the cable and then back out. I mean, it makes it a big antenna, but the ground in the PC will have suppression. The ground on the device should have suppression, but that's not always the case, as we're about to demonstrate. The shield is essentially designed to be an antenna, right? You want the shield to absorb any external signal without it reaching your signals. If you had, for instance, if you had a faulty ground wire in the USB cable, it would then use the shield as ground, which would be really bad because now you're using an antenna as ground, and you're coupling all of that noise into the entire system. So that is possible. But generally, the shield on the outside breaks on one end well before that happens. So we don't have to worry about reset. We've got test. Let's look at these oscillators. So it says here, look at note 2. It can be left unused. So for details, it will show you section 7.6. So let's look up 7.6. Yeah. Oh. Well, Control F has failed us. Oh, and yeah, there's an error in the data sheet. Yeah, there we go. External oscillator. It would have been great if they had left us a schematic example for using an oscillator. Another common thing we can do with boards like this is we can look up like I know for a fact that SparkFun has a board that does precisely what we want this to do. So we're going to cheat a little bit and we're going to copy off of someone else's work. But that's what open source is, right? Building off of other people's, yeah. So if we go into the document section here and we open up the schematic, we can see that they are using the FT232RL. They have test tied to ground. They have VCCIO tied to power, which is on a jumper link. But we can see that they didn't use the oscillator. So in fact, if you read the data sheet real quick, it says that the chip defaults to using its internal oscillator. Basically, what it would mean is you would have to program the EEPROM inside the FT232 to actually tell it to use an external oscillator. So in this case, I guess we're going to omit the external oscillator because for a board like this that has no firmware, requires no programming, essentially you assemble it, you test it, and it just works, is kind of like one of the holy grails of electronics, because having to do the hardware and write the firmware for a project it gets tedious fast. So we're going to omit, and this is why the data sheet for a chip is supremely important to designing with it. We had a goal in mind of what we were going to do, what we wanted to do. We read the data sheet and we saw why that isn't necessarily a reasonable thing to do. When you're designing a project like this, the goalposts will move on you whether you like it or not. Now, this could be, for whatever reason, this goalpost moving could be game over for us. We could decide that that goalpost moving is unacceptable for our design parameters. Like if we say we absolutely 1000% need to have an external regular or oscillator, then you find a different chip. But in this case, it's, if we look, this is an established product doing the same thing, and it works just fine. So we're going to do the same thing. So if we go back to KiCad, we don't need to do anything with the reset pin. We don't need to do anything with the oscillator pins. We've taken care of power. We've taken care of USB and ground. The only thing that's left is the actual serial part, which is 2 more pins. So if we look back, do a little bit more cheating, we can see that they tied some of these signals, like there's a transmit and a receive LED that we could hook up, but for the purposes of this project, we're the default. These GPIOs down here have a default action and a configurable action, so you could potentially configure some of these other pins to be the transmit LED pin, but again, that would involve programming the chip. And
those are the same as the C bus on ours?
correct. Their symbol is just named differently. They've, instead of calling them C bus, they've given them the default behavior. Well, that's a default behavior. So out of the box, unprogrammed by default, those will flash when you transmit a byte or when you receive a byte. We could do those LEDs, but for right now, I just want this to be as simple as it possibly can. And honestly, if we had done the 5-volt version, it would have been more simple, but we want it to be simple and usable. Now, I also want this to be something that we could order and fabricate and have it work and have a working product in our hands. Not that we're necessarily going to do that, but we could. So again, we can see the CTS and DTR pins are connected, and I think it's actually the DTR, the data transmit ready pin that's used for reset in the sort of Arduino world. But like I said before, we're going to ignore all those signals, and all we care about is transmit out and receive in. The direction on those is important because what you're connecting to also has a transmit and a receive. You have 2 pairs of transmit and receive. You want the transmit of one to go into the receive of the other, and vice versa. Because if you get it backwards, it's not going to work. Not going to break anything, but it's not going to work. So let's go ahead and... So the pins that we need are power, ground, transmit, and receive. So let's drop a 4-pin connector. Go back into our... And then because I know what it's named, I'm going to type it instead of searching for it. So type in CONN _ 01 X04. And then I like to use just the generic connector, but you can see there's a couple different options. It doesn't really matter which one you use because the actual footprint part of it we're going to set later. And the only reason why I didn't go through and manually select that is because, as you can imagine, there's about 1,000 different variants in connectors that are loaded into KiCad, so it takes a bit. And it's funny because the Windows version of KiCad, I don't know if anybody here is using it, but the Windows version loads way slower. And that's because when you open the symbol library or the footprint library, KiCad says, okay, Git, fetch the latest repository. So every time you use Git, every time you open the symbol window, it makes sure that it has the latest and greatest from KiCad themselves. It's actually pretty nice. To my knowledge, there is no other CAD platform that will do that. Like you actually have to go into your library and say, update this. Now, for Windows users, that's kind of a hassle because Git is extremely slow on Windows, and yeah. So now that we have this 4-pin connector, let's just arbitrarily say that I want pin 1 to be voltage and pin 4 to be ground. We're designing this board. We can make it do whatever we want as long as it's within the parameters of this chip in the datasheet. If it's capable of doing it, we can do it. So this is the reason why previously we had created this 3.3 volt symbol. It wasn't necessary then, but now since we want to break that out to the target, it is necessary. So we're just going to wire these up real quick. And then again, arbitrarily, I am going to go ahead and highlight all of this. So if I highlight all of this without pressing a button, KiCad is just going to move it. I'm just going to go ahead and line that up and arbitrarily say I want transmit on pin 2 and I want receive on pin 3. You don't have to do it the same way, but that's just how I've chosen to do it. And right there is our complete schematic. Now, technically speaking, this is not correct. And what I will tell you is that it's the CC pins on the USB-C connector. Now, technically, to be a proper power sync, which is the nomenclature that USB-C uses, we have to have resistors on those pins. I'm just going to look that up really quick. I believe it's either 5.6K or 56K. Okay, as you can see, I've been here before. Yep, 56K. So we see here current source capability, default USB power, which is going to be default for the controller, but it's usually 500 milliamps. We can see pull up to 4.75 to 5.5 volts. And what we're going to do is we're going to pull the CC pins up individually with their own individual resistors up to the 5 volts from the USB port. So when you have a pin, like an input pin or an output pin, and in this case the CC, I believe it's a configuration control pins, are outputs. And the controller first, there's several modes that the controller operates on, but the first mode that it does is constant current mode. And it will set the output current of the VBus pin, the 5 volts pin for your board, based on the current that flows out of the CC pins, or in this case into. Anyways, pulling means you have a pin, and instead of letting it float connected to nothing, that's the term, is floating. And what can happen on a pin that's floating is electrons from the air can actually affect the charge on that pin, and the voltage on that pin quite literally floats. So what we do is it's called pulling. So if you had something pulled down, you would have a resistor connected to that pin tied to ground on the other end. And what that would mean is that, say in that case you had an electron was able to affect the charge on that pin, that charge would then immediately trickle down to ground through that resistor. There is some resistance, some path for current to flow. It's not just high impedance. And I know there's that impedance word again, but just kind of think of impedance as resistance, even though it's kind of completely wrong. But in layman's terms, that's what impedance is resistance. And so to pull something is to give a path for current to flow. You either pull up or you pull down or you pull to some specific voltage. Correct. Correct. And there's no really specific voltage that is up or down. Generally speaking, if it's connected to ground, it's down. If it's connected to anything else, it's up. It's just kind of how, the nomenclature. Anyway, so if we look at the chart, there's a bunch of different specifications at different voltages, but what we're working at is default power at 5 volts, and that's 56K. So what we're going to do is we're going to go back to here. And I don't know if you guys have heard about the newest Raspberry Pi with USB-C port, which is technically not USB-C compatible. And the mistake that they made is they tied both of these CC pins together with one resistor, which is wrong. It is invalid to the USB spec. So what we're going to do is do it right, and we're going to use 2 individual resistors because there's 2 CC pins, again, for mirroring. If you have them tied together, then the way that the controller works is one CC pin is there's actually digital communication over these pins. It's one of the modes. And if you have the 2 pins connected together, it makes that digital communication mode invalid because it's essentially loops back into itself. So what we're going to do is not that and do it the correct way. So we're going to go back into add a symbol, and this time we're just going to type R, and you get the standard old box resistor. And I'm just going to add 1 down here, and then I'm going to hit V to change the value to 10K. And anyone who has a full numpad can use Alt-234 to type the ohm symbol. Ask me why I know that. And then I'm just going to move these capacitors over so that there is room for these 2. Come on. Yes. So in fact, so all the technology that basically you'll work with today is based off CMOS, which is complementary metal oxide. If you've ever heard of a MOSFET, it's a metal oxide. So there's like an almost atomic thick layer of metal oxide separating 2 doped semiconductors, and that's how it actually functions. So if you have static high voltage, you can actually punch holes in that extremely thin oxide layer. That's how you damage these chips. So basically what happened was they realized that these devices are so sensitive, so what they started doing was building in protection devices into each pin. So each pin has a transient voltage suppressor. It has clamp diodes. It has, there are chips that are not like this, but in general, unless your datasheet says you must, like the test pin, you must tie this to ground, or this pin must be pulled high, then you don't have to worry about it. Now, this is in the digital domain. If we were talking like operational amplifiers in analog domain, you kind of throw the book out. Everybody says analog is black magic, and it very much is. Not really, but. So we've got our 2 resistors in, and all we're going to do is we're going to tie one of the resistors to CC1 and one to CC2, making sure that we are completely compliant with the USB-C spec. And then we're going to tie both of those to the VBus pin. Again, if we had some protection devices in place like transient voltage suppressors, voltage clamps, fuse, we would put these connections after all of the protection devices. That way, when these resistors aren't connected, the controller is going to go, oh, my device isn't connected anymore. Let's stop dumping current into it. So if say, your fuse trips on one end and that end is dead, you don't want it to look like there's still a device connected. anyways, we're not doing any protection. We're not doing any safety. If we mess this thing up, the blue smoke's coming out in a hurry. You're right. Good catch. See, that's why we do design review. Because if you put a 10K in here, let's go back to that page, because if you put a 10K in, you're getting 3 amps potentially of delivery output. Well, USB-C can technically do 100 watts, I think, which is 20 volts, 5 amps. So if your controller is rated for it, you could potentially draw 3 amps. I mean, it would deliver 3 amps. You wouldn't necessarily draw it, but if there was a malfunction on your board and it said, okay, here's 3 amps, the blue smoke's coming out in a hurry. So that's the joke with electronics. The joke is that the blue smoke is an active ingredient in all electronics. If you let it out, they stop working. It's Well, black smoke is worse than blue smoke because black smoke implies a very rich combustion, and that is quite a lot worse than just some blue smoke. Let's see. Yeah. Well, no. So the blue smoke that you're seeing, yeah, yeah. So the blue smoke that you're seeing is most modern integrated circuits are encapsulated in epoxy. The black casing is a plastic epoxy. It's thermoplastic elastomer, which basically means it doesn't melt, it burns. When the blue smoke is let out, it means that some circuit in the die has gotten so hot that it literally ignited that plastic case. But because we're talking about pieces of metal that are so thin and tiny, they get hot enough to burn and then they vaporize. So it gets real hot real quick and then it's done. And so a lot of times you'll see what's called a crater. It looks like a crater in the actual package. Let's see if I can. Let's just bring up some Google and we'll see. Let's see if we can. Right where? Yeah, but there's no real good shot of. There's another word that people like to use for this kind of phenomenon, but it's not exactly family safe, so I won't use it. But yeah, you can see scorch marks. Parts of the package are physically missing. We're talking about potentially high energy events here. That's when the black smoke comes out. You actually have combustion of the material itself. The TPE, the thermoplastic elastomer that it's made out of, this is actually kind of like a 2-part resin. It's designed to burn and not melt, because if you melt the case off your IC, you expose the die. Anyways, these things are rated to like 120 C. Most plastics melt way below 120 C unless it's a thermoplastic. Anyways, you have heat enough for combustion, but it was such a short period of time that it's just a little.
Essentially, the vaporized metal gas is looking for a way out, and
Yes.
it will usually punch a little pinhole
Yeah.
to get out.
Yeah. So the surface of those chips is cratered like the moon, so it finds a structural impurity, essentially a weak point, and just pushes out. If we're talking about MOSFETs of that size, they have ones that are like quite large and heavy. We could be talking about hundreds of watts going through one device. If it has a failure, it can physically detonate. It could potentially, like 3 amps at 5 volts is 15 watts, and most packages have a degree C per watt rating. And it's usually for the package we're dealing with is usually like 72C. So that would be 72C times 15 watts would be a lot. But like I said, we're talking about small connections, 15 watts over, a piece of metal that's thinner than your hair. That amount of energy would end fairly quickly. The other USB pins here they're called, I believe it's sideband or something like that. Those pins are really only used if you're doing something like DisplayPort over HDMI. It's essentially extra pins for extra protocols. And I believe the sideband pins are your horizontal and vertical sync for DisplayPort.
Would this USB-C port be a Thunderbolt port if you like wired it right, or does that actually have extra pins?
Well, so Thunderbolt physically is USB-C, but much like RS-232, Thunderbolt is a spec on top of USB-C.
But does this right now have all the pins
No,
for Thunderbolt?
no. So this symbol doesn't actually show you any of the USB 3 pins. If I go back into here, come on, KiCad is a little annoying sometimes. So if I type this in here and we do USB-C receptacle, this will list all of the pins in the USB-C spec. Basically, the pins that are missing are the super speed, RX1, RX2, TX1, and TX2. Those are the differential pairs.
Okay, so there are a bunch of pins that weren't just not.
There are a bunch of pins, and theoretically, for something to be Thunderbolt compatible, you would have to have a USB 3 controller, but B, have those pins connected. Correct. This would be USB 2, and the connector that we're going to pick that in a minute is actually a USB 2 only USB-C connector. There are physically less pins. Makes it easier to solder, makes it cheaper. So much better. There's like literally less than half the pins. If you've ever seen a USB-C connector with all of the 3 pins, they're so small and narrow. It would be actually they have 2 rows. There's a row of pads underneath the connector and one behind it. It is physically impossible to solder by hand. USB 2.0 only have 1 row. Totally possible to solder by hand. Love them. Great. So we've gone through the data sheet. We've looked at all the pins. We've identified ones that are not a requirement for us and pins that are required to be connected. We're at a point where our schematic is more or less done. So our next step is we have to annotate, which is this thing here. It looks like a piece of paper with a pencil on it. And this is the thing that I was talking about earlier that allows you to assign all the names, the reference designators to all of your parts. There's nothing we need to configure in here. The only thing that we need to do is hit the annotate button. And if you look in the back, now all of our parts have a proper name. C3, C2, C1, U1. And unfortunately, the way you laid out your schematic is going to determine the name of all of these parts. So if your schematic looks physically different to mine, your names are going to be physically different to mine. So I'm going to try and not refer to my components directly by name without showing you precisely what part I'm talking about. But yeah, if you look at the options here, it will tell you how it's naming all of these, whether it goes right to left, top to bottom, that whole thing. Once we've annotated them, the next thing that we have to do is we have to assign our footprints. This is the physical part. So our symbols are the logical part. It's the thought of the connection. It's not the connection itself. So what we have to do is this that looks kind of like the symbol behind the footprint. It's next to the bug. We're going to hit that, and you might get a really, really long loading screen if you're on Windows or have a very slow hard drive. But So this list in the center that you can see is all of our parts. We have all of our capacitors, our connectors, our resistors, and our chip. And what we can see is there's a colon, and after that colon is the package, the physical part. The only thing that has that is this FT232RL, and that's because the FT232RL will only ever be in this package. The part in the library was designed with this package. But our resistors and our capacitors, they're generic enough that we can say, oh, I want this size or I want that size. So we have to assign it manually ourselves. So let's... Didn't change them. Good catch. So I'm going to go ahead and hit V. 56K. I mean, what's 15 watts? All right. Yeah. All right. Let's go back into this. Nope, you only have to annotate once. The only time you have to re-annotate is if you add parts. So, and the other thing is if, so let's, for example, I'm going to close this, and I'm going to add another capacitor just by copying one of these. You get your C question mark. You don't actually have to hit the annotate button. If you hit the footprint button here, it's going to say, oh, well, you got to annotate it. It kind of knows the steps and will catch it for you. There's a fair bit of automation.
Can you force specific annotations? So
Yes.
want something to be C2,
Yes.
C2 then
So
annotate?
I believe if you do, I think it's the N key. No, it's, let's see, properties. Edit reference. It's the U key. So if you go over and hit U, it will do that. And then if you open the annotate window, it has an option that says keep existing annotations.
Okay.
So if you've already annotated, or if you know you specifically want this part to be this, that's the default. Just leave it ticked, and you don't have to worry about it. It gets a little bit weird because you'll have 3 or 4 revisions of the same design, and between those revisions, you'll have added and removed parts. And then your whole XY setup gets thrown out the window if you keep existing annotations. So a lot of times what I like to do is once you've gotten to the revision you're going to order with, reset existing annotations, and then just clean slate. And then do a final design review, submit, do the whole thing. And now, a lot of times that design review may be you doing it, but what I like to do is have at least 24 hours between when I finished working on it and when I go back through looking at it, because you have a clean head. You haven't been looking at it for 10 hours. Anyways, so now we have it annotated. Let's get back into here. So we have these capacitors that we know are capacitors because they're called C. Let's see, capacitor, we know that they're surface mount, not through hole. I don't know what the T stands for. Do you know what the T stands for? THT, through hole technology? Yeah, technology. And then, of course, they went with surface mount device. Whatever. Anyways, so I know off the top of my head what all of these sizes mean, but basically, these 4-digit numbers are the size in inches. So an 0201 is 0.02 inches by 0.01 inches, basically grain of sand sized. I find that for hand soldering, 0.08 by 0.05 is a fairly good size. It's about half the size of a big grain of rice, like a big fat brown rice. Like half of that is an 0805. Pretty easy to solder. So I'm going to go with capacitor C0805 hand solder. And basically the only difference between the hand solder and the regular version is the pads are a little bit longer. gives you more room to get an iron in there and actually solder it. I like using them. They're whatever. It doesn't really matter. Mm-hmm.
You have to scroll down.
So what's going to happen is I'm going to double click this that I have highlighted, and what it's going to do is it will fill in over there and then move down to the next part. So what you can do is you can just sit here and you can say, oh, let's just make all of the capacitors 0805. You would think that you could highlight them and then double click and it would fill them all in, but no, it's another user experience issue. But I'm just going to keep double clicking until I've got to my J1. Now, if you notice, while I have these capacitors selected, there's a whole bunch of options on the side. But if I then go and select this USB receptacle, our filtered footprints on the right side have disappeared. And that's because we have filters on. So up here, these selected buttons, and you may not have these selected. If you look up here, these four here, these are our filters. And they allow us to filter by a partial name or pattern, filter by the library, so whatever we have selected over here. So if I unselect that, we're just going to get a ton of, well, maybe not a ton of parts, but we can do filter by pin count. Anyways, I find it's good to leave all of these filters on. The other thing that you can do is if you know that like our USB receptacle is a fairly niche keyword. It's not like voltage regulator, of which there will be a billion. We can go ahead and this one here that says filter by the selected library. So basically what this is going to do is include all libraries. Well, now we've just got 3. So I think through hole right angle. Yeah, USB-C 2.0. So I'm going to go with this HRO Type-C 31M12. Well, I guess there's 2, but it's that middle one there, the H, I think it's HRO.
Click it on and click it off, and it comes for some reason.
Another good example of what I was saying before is this connector, the 1x4, fairly generic. So we have quite a lot of options over here. But I can already tell that it's not a Harwin, it's not a JST, it's not a Molex connector. We're just going to go down to the generic pin headers. And then I'm just going to select the vertical 2.54 millimeter 1x4. That's like a standard pin header. 2.54 millimeters is 0.1 inches.
Why are capacitors in inches and...
Don't worry about it.
Okay.
Well, if you go to the capacitor, you can see 2012 metric. That's 0.2 millimeters by, no, it's 2 millimeters by 1.2 millimeters.
Okay.
So it's listed in metric and inches, but there are several cases in electronics where you will find that mix. Like, for instance, a lot of times your track, your actual wire on the board, those are measured in width of mils, which is 1 thou. But your via, your pad diameters are measured in millimeters. Why? Anyways, KiCad likes to do a lot to do one or the other, so it defaults to millimeters for track width and hole sizes. So for anyone that learned it in mils, it's kind of a big difference because you don't know necessarily what you got to math it basically. until you get a feel for it. So what you send the fabricator is a Gerber file, and the Gerber file has its own internal units, I believe, or you can tell it units. It might be inches. You can tell KiCad how you want it to export it. But yeah. So I'm gonna do the pin header 2.54 millimeter vertical 1x4, and then again for our resistors, we are gonna get a bunch, and then I'm gonna go for the R0805 hand solder for both of our resistors. And then, unless you've added a bunch of extra parts, that should be everything we need. Of course, we could have added some LEDs, some more resistors, maybe a reset switch. KiCad is usually really good. They're built-in library parts. If you're going through, like, say I want a reset switch, and I find one, oh, this looks nice, it's a good size, it'll contain like a DigiKey part number where you can go and look up where to buy it, so that when you make your bill of materials, not only does it have the part, has the quantity, but potentially has where you can buy it, the price, everything you need. Yeah, the integrations for KiCad, a lot of that I haven't gotten into yet, but like it's all, the integrations are crazy. Like there's I believe they're called Octopart. Octopart is like a central repository for all of the distributors. So they maintain a database which is plugged into DigiKey and Mouser and all of the other distributors. So you can they build a tool for KiCad that allows you to generate a bill of materials. But while you're generating your bill of materials, it reaches out to their service and says, "Here's my list of parts. Find where it's cheapest." And it does it instantly and dumps it in your lap. Like all stuff you had to do manually before, reach out to all these distributors, potentially call your rep. Yeah, you just give up. And normally it's just DigiKey because they're the most pleasant to work with. But by far and away not the cheapest. So now we can see, if we look at all of our parts, we have all of our footprints assigned. That's what we want. So down here, there's this button that says apply, save, and continue. If we had hit, so like when we hit this button, then the annotation window came up. It will do like that chain. This is the button you would want to hit to go to the next step. But I'm just going to click it anyways because it'll actually save our schematic. I don't have to exit and hit Control S anyways. So now, no. I mean, it doesn't close the window. Yeah, another user experience. If you're in the chain of windows, it closes it, but not in this case. There's a lot of little things that you'll notice like that. But as it currently stands, our schematic is done. Don't worry if it doesn't necessarily look like mine, but in general, the more you do this, the more readable, human readable, you want your schematic to be. Because the only reason that the schematic exists is to be human readable. You know what I mean? If it's not done in a human readable way, then why do it in the first place? Other than the fact that it's required. Anyway, so what we're going to do is we could go back out to the KiCad main window, because if you notice that that's still open, we could go back and we could open the PCB editor, and then we could manually import everything. It's the button that looks like a circuit board. You could click that, but that's more work. We're going to do the short route. And there's this button here, which is identical to the one in the main window. And it says Run PCB New. And PCB New is just the name for the circuit board tool. So I'm going to go ahead and click that. And you can't see that window because it popped up. So right now we have no parts. There's no communication between the schematic and the board. We have to import those changes essentially. Now one of the things you can do is, if we go back to the schematic, one of these buttons here looks like a, I don't know, looks like an X with a net. It says generate netlist. That's kind of like the old way of doing things. Basically, it creates a text file with all of those nets that I was saying before, all of their names and all of the places that it's connected, and then you import that. If we go back to the PCB new, there's another identical button here that says import netlist, load netlist. That's like the slow way of doing it. Like it creates an actual file on a hard drive and then you import it. It's nice because if you have some sort of like external verification tool that you feed a netlist and it thinks about and gives you some answers, then you may need to do that. But KiCad also has a way, if we go tools, update PCB from schematic, it's gonna, I've clicked it and it ran it. And what this is it's like a pre-run. It hasn't applied anything. So you can see, it's added a bunch of footprints. If we go back into our schematic and then delete something, it will say delete. These options here delete extra footprints. So if you have a specific footprint for like say you've made your Twitter handle as a PCB footprint, and then you add that to your board, if you click delete extra footprints, every time you update your board, it's going to delete that. So, but at the same time, if you delete a part out of your schematic, it's not necessarily going to delete that part on the board. So it's kind of like a foot gun situation, where sometimes you're doomed if you do, sometimes you're doomed if you don't. Just, I would say every time you click that update button, you think about what's going on. Because if you send a board to fab with extra parts on it and you get it back, it's like, why the heck did I do that? Design review. It's all about design review. Anyway, so we see no warnings, no errors, netlist update successful. So internally it generated that netlist, fed it into PCB new, thought about it. It's okay. Everything's kosher. Update PCB. And then when that's done, we can hit the close button, and you'll see that at your cursor is all of the parts that we created. So there's the USB-C, there's the chip, there's all of our resistors, there's a capacitor, and there's our connector. Yay! To be honest, you might think that electronics is a bit glamorous and that the majority of the work is what we're about to do, but the truth is far from that, and that is the majority of the work is reading the datasheet, design verification, and then putting it on the board. Possibly breadboarding in between. Yes, you could get like some USB-C breakout boards, a breakout board for this chip, make sure everything works. But the prices of circuit board prototypes being what they are, and this being as small as it is, you would probably just order it. You have no BGA packages, no hidden pin packages. You have access to all of these pins. So if you have to put a bodge wire on there, which a bodge wire is a fix for a problem that you created, if you have to put one on there, you can. You can get them made mainland US, $5 a square inch. So for this board would be maybe $10 for 3 boards delivered. China, we're talking maybe $1 a board delivered. So for a small run, like if you're getting 5 boards, I've seen as fast as 2 days from China. Yeah, so basically from China you have 2 shipping options. You have the slow boat and DHL, and DHL will light speed it through the earth at you, but they will also charge you $30. The slow boat is a boat. Literally a boat. Anyways, I have never once had a problem with customs with DHL. I have never once had an issue with a lost package. I have never once had issues with insurance. DHL is like the most professional company I have ever worked with, hands down. Anyways. Sometimes, yes. So all these little lines that you can see flying around, going through things, all of these lines are called a rat's nest. And I'm sure you can see why, because if you have a board with 1,000 parts on it, there's possibly 5,000 lines on your screen. So one of the things we can do is, if we look on the left-hand side, we have this button here. Looks kind of like an X with some dots. It says Hide Board Rat's Nest. If we click that, that all goes away. Another thing we can do is, there's a lot of text here on the screen that we don't necessarily care about at the moment, like the gray text. Let's go ahead and turn off FFab. And that's going to reduce the noise that we're trying to see down to a bare minimum. So we know what the part looks like clearly we know what the USB connector is, what the chip is, what our resistors and capacitors are. It makes them easier to move around and position in a way that not only will look good, but in terms of layout, running all of our copper traces will work out. So what I like to do is I like to start with our the main connectors of our board, whether it's power connectors, USB, whatever. And in this case, it's the USB-C connector. So if I hover over it, hit M to move, and then R to rotate, logically, when I lay out a board, I usually like to do left to right in order of, let's say, precedence. There's also a lot of people that like to do top down. So instead of their USB connector off to the left, it will be pointing up and would be logically straight up. So you have something straight up and down. But the way I see it is, your monitor is widescreen, not tall screen. So you see more content if you have a wide board versus a tall board. You know what I mean? Anyways. So what we're going to do is, I'm not even really measuring anything at this point. Well, really the only thing that's important here is the spacing of these pins, so that when we whack a header in there, or a cable or a wire or whatever, it's right. Other than that, we don't really care. Now, if you wanted to make it look really, really nice, or you wanted to, I don't know, adhere to some spacing standard or something, you would align this to a grid. And you can't really see the grid very well on this computer. Something about the graphics chip makes the grid render weird, but you can see how you have your primary grid that's spaced out at 10 grid points. Those are the bright dots, and then you have the dim dots. We can see up here our grid is 0.1 millimeters. So about the thickness of a human hair. You can use the N key, N as in Nancy, and you can see my grid's going down. Oh, well. And you can also use Shift N to go back up. So all the way down to 0.01 millimeter, which is, ridiculously tiny. I usually like to keep it 0.2, 0.25 millimeter. That's a good minimum resolution. But, with the N and Shift N, you can be constantly adjusting it. Anyways, what I'm going to do, so I'm actually going to turn our rat's nest on really quick. And I'm going to take a look at, oh yeah, I completely forgot something. So in KiCad, you can route something that's called a differential pair. Now, what's a differential pair is kind of outside the scope of this talk. Just know that a normal signal, like the reset pin or like the transmit pin of the UART, those are single-ended. you have a single pin that says I'm high or I'm low. A differential pair has two pins, one that's low and one that's high, and they're logically mirrored. And the transition of those two signals going high or low, whatever direction that may be, indicates a 1 or 0. It's kind of complicated, but basically anything that's a sufficiently high speed, SATA, USB, USB 3, Ethernet, HDMI, DisplayPort, all of those things are examples that use differential pairs. Since you have two signals that are coupled, you have what's called a really high common mode noise rejection. So basically, any noise that happens on one signal happens on both of them. And because you're monitoring the hard transitions between those signals to indicate a 1 or a 0, any common noise is ignored because they both twiddle at the same rate. There's no cross. You get what I'm saying? If you had one signal and there's noise on it, you can't tell whether it's actually going transition or it's just got a lot of noise on it. So it's a immunity thing, it's a speed thing, it makes a lot of things better. Anyways, to route however you say it, route a differential pair is it's kind of it looks very specific. This impedance word is going to come up again.
This is the same as the twisted pairs that you see in like Ethernet cables, right?
Correct. Ethernet's a little bit different because it's fully isolated with a one-to-one transformer, but we'll kind of gloss over that. The twist actually does enter into it. It ensures that any noise that's received by the cable is in fact common mode noise. When you twist the cable, you form both signals, both conductors, into the same antenna. If you had them running side by side, there's a chance that one conductor could pick up noise that the other conductor doesn't, in which case it would no longer be common mode noise. Your common mode rejection would fail, and you could potentially get crossing within the two signals. So the act of physically twisting them does actually have quite a big effect. Anyway, so if we look, actually I think this is probably a good image. I can get a big enough. No, come on, you're killing me. Basically, it's you have to route them in a way that the impedance requirement of the signal is matched physically. So if you've ever looked at a circuit board and you've seen traces like this that are all squiggly and close together, they do that to meet the impedance requirements. And what we're seeing here is actually a GIF of them meeting length requirements. So we know that an electrical signal travels along a conductor at about 5 picoseconds per millimeter. That means that if your clock rate is sufficiently high, a length of even a difference in a millimeter can cause a great effect. Anyways, we have to route the USB signals as a differential pair. And KiCad can do that for us. It's kind of default setup to do it correctly. So, but there's one thing that we have to do in KiCad to actually do that. Let's go back into the PCB editor. And it's going to get really angry, but I want to show you it getting angry. So if I go route, differential pair, and I just click any old signal, it's going to say, I can't well, it's going to say that, but if I pick a pad, yeah, you can't start a differential pair in the middle of nowhere. You have to pick an actual signal. If I pick a signal, it's going to say there's no complementary signal to our pair. We have to name them appropriately. We must end with an underscore n or a plus minus. I like the plus minus because I think it looks better. So let's go back here. And I'm going to hit the L key on my keyboard to create a label. I'm going to make a label called D plus. I'm just going to plop it down on there. And I'm going to click there, and I'm going to make one called D minus. Now, what we've just done may seem like not anything at all, but what we've actually done is we've told KiCad that these are in fact differential pairs and should be treated as such. So now we go back into our PCB editor, and one of the things that we'll be able to see, actually we have to update. So if you make any changes in the schematic, you have to update. It doesn't do it automatically. It's kind of a pain in the neck. Anyways, so if we look in here, we see reconnect some net named whatever to D plus, D minus, update successful. So we'll do update PCB and close. If we look at these pins, they now physically read D minus, D plus. Cool. So what we want to do is we want to identify where these signals go on this chip because it's important. We want these signals, A, to be as short as possible, within reason, but B, not cross any ground planes or do anything weird like that. We want to have it essentially isolated from things. So what I'm going to do is, once we have our USB port in a place that we like, I'm going to move this chip in such a way that our USB signals can get straight to where they need to go. So if we look, if we imagine there's a corner here, D minus is on the inside of the corner, and D plus is on the outside of the corner. It's important to remember because you don't want the two differential signals to cross, like physically. Like if you have to put a via down and then jump over, that's okay with a normal digital signal, but what we want is we want this to go up and over. No vias, no weirdness, it just connects straight over. Via is just a hole. It's a plated hole. Just like you would mount a connector to. That's the distinction between a pad, which is part of a component, and a connection that's part of a wire. That's just a naming convention thing. But yeah, so if you imagine wires coming out of that and connecting over those pads, you can see that they connect directly, and that's important. That's what we want. It goes under the chip, not ideal, but it's better than the alternative. So what I'm going to do is I'm going to go route differential pair, and then I'm going to click one of these signals. Now, you'll see that because of the way the USB-C connector works, there's actually two D minus and two D plus, which is kind of throw a hammer into our whole differential pair thing. But we'll cross that bridge in a second. But you can see D minus is going right straight to D minus. Perfect. This is exactly what we want. So I'm going to zoom in. I'm going to put that about as close as I can. And then for reasons, maybe go down a couple of grid spacing. Get it lined up nice. Once you've got it placed like that, in order to actually get it into the pad, you have to then exit differential routing mode and go into single track routing mode. And then we click in there, and we could make it look nicer, but yeah, let's actually. Honey. Let's give it a shot. Well, it's because KiCad gets changed all the time. You'll notice that there's features that weren't there before. So let's just try that. We'll go into the center. Yeah, looks like it. So there, boom, done. Did it for us. Now, you have to keep in mind, USB has a very specific impedance requirement, and that impedance requirement is going to be based on the specs of your circuit board, which KiCad doesn't know unless you tell it, but we don't know because we haven't ordered it, and there's a lot to worry about. But in this case, USB is a little bit more like USB 2.0 is pretty bulletproof. As long as we route it like this, it's going to be fine. It's 100% not the right way to do it, but the tolerances on USB 2 are such that the impedance doesn't matter as much. Like if it were USB 3 super speed, it's going to matter a lot more. You know, you have to do length matching, you have to do all these other things. If it were DDR3 memory, would matter a lot. USB 2, 48 megahertz, quite slow. The faster your signal is, the more the impedance has an effect on that signal. The 45-degree bends could potentially cause a problem on a signal that's a 2 gigahertz signal. Because physically what happens is you have a current that flows from one node to another, but along the way, you can get reflections of power back towards the transmitter. That's why if you see a hard right angle bend in a circuit board, you know, you may not think much about it, but an electrical engineer would see that and cringe and go, why? Why would they do that? So one of the reasons why KiCad will maintain a 45-degree bend is because that's a good compromise on signal integrity versus bendiness. That's why if you look up, if we go back to our image here, you can see those are nice and round, nice and curvy. That causes very minimal reflections, and the radius of that bend will be based on the frequency of the signal. You know, it gets really, really in depth. The electrical engineering is like, it gets really crazy really fast, but it's kind of out of scope. Anyway, so we have our USB routed. Where's my mouse? There it is. Yes. We have to that's the next step. So if we look, we have this D- and D+ that need to be connected to the other two. So this is actually kind of a sticking point, and most people don't really understand why Intel designed the connector in such a way that they don't connect internally. Because what we're about to do technically violates the whole differential pair thing, but like I said before, USB 2 is so slow. There's a thing in electrical engineering when you add what is essentially a useless section of copper, it's called a stub, and that stub is essentially, it creates parasitic capacitance, parasitic inductance, but bad things basically that affect the impedance characteristics of the bit of metal that you're working on. So in the example that I said before, like when you want to overlap the 250 ohm resistors to select an antenna, the reason why you overlap the two pads is to avoid the stub, the useless bit of metal that's resonating at the frequency and affecting things and making things worse. But what we're about to do is create a stub. So when the plug is in one way, you're going to have a bit of useless copper connected that's flapping in the breeze, and when it's connected the other way, it's actually integral to the connection. You know what I mean? So in one orientation, your cable will be connected to this D+ and D-, which are going to go through a connection to our actual differential pair. But when it's in this orientation and connected to this differential pair, the connection to the other set of pins will be flapping in the breeze. It'll be a stub. Bad. But it's slow enough that it's not going to cause problems. So what I'm going to do, if we go to route here, we see single track. It says Shift X, but I know it's actually X. Or maybe it is Shift X. It was Shift X. So what I'm going to do is I'm going to start D plus first because I know I want to put a via in. And if you press F, or V, place that via as close to that pin as possible. And now, so red is top copper, and if we look at our color chart on the right, we can see green is bottom copper. So when I started that track and I hit V, V is the key to change layers, it created a via and dropped me down to the bottom. And for right now, I'm going to escape. And if you see the little blue arrow next to the bottom copper layer, that says I am currently on bottom copper. So if I draw another wire, it's going to be on bottom copper. With no, in the top right, see the layers manager, the little blue arrow? If I hit the V key, watch that area when I hit the V key. It switched to top copper. And now if I click, it's going to be on top copper. So what I'm going to do now is I'm going to try and run. And see, this is KiCad's automatic routing. It says there's not enough clearance to sneak that trace out that way. But if I go around the back door, so then we know what we've got to do is we've got to move that via out in such a way that we can sneak a trace out, but it's still as close as possible. So close. There's a better way to do this, I'm sure, but it's the way I do it. Like, I guess you could run this D minus first. And all I'm going to do is I'm just going to go around it like that. And so we have our stub. So if you look, like I said, if this, your connector is plugged into the orientation where it's connected directly to pin B7, sure, it's connected right directly to that differential pair, but now it's also connected to A7, which is connected to nothing, and flapping in the breeze. You won't see anything like this on any of the super speed pins because they're too fast and it causes all kinds of problems. So the other thing that I'm going to do is I'm going to go to B6, the other side of that signal. And now see there's clearance issues over here too. Because of course there are. So if you highlight a section of a trace, come back. There we go. If you highlight a section of a trace and hit delete, it'll delete just that section. But if you hover over a whole thing, it will just delete that whole area. Anyways, the idea is to keep this loop as physically small as possible, because the bigger you make it, the more parasitics you introduce, the worse the signal integrity. And it's slow, but it's not that slow. There's still concerns. Just going to try and move that out. Oh, there we go. So we can sneak that trace out. We've got that there, and now they're connected on the bottom side of the board. So now both of our D minus and D plus are connected by the shortest possible wires that we can make. Now, you also have to remember that even though the via is there, you have to perceive that it has depth. And that depth is whatever the thickness of your board is. So you have to add the depth of that via to the overall length of that signal. Another cardinal rule of differential pairs is if one signal has a via on it, they both have a via on them. You know what I mean? Thou shalt put vias on both signals. If you do something to one, you do it to both. So that's why a lot of people were like, what are you doing? But again, Intel knows the science. They did the math. They figured out that this is fine. So this is what we get. So the next thing that I'm going to do is I'm going to go back to our schematic and look for these 56k ohm resistors, which are the only two resistors I have, R1 and R2. And then I'm going to go back into PCB new. I'm going to locate these two resistors. And then I'm going to see how the rat's nest changes. So we can see that one side is connected to, what is that? B9 and A4. I know that the two outside paths are power and ground. They don't say that because reasons. So I know that A5, what is that? A6 are R2 CC pins. So it's not actually super critical that our two resistors are beside those two CC pins, but I kind of want it relatively close. Because again, we know from the USB-C spec that those can carry digital signals, and signal integrity being what it is, let's leave it as short as we can within reason. Now, if it were me working on a real project, I'd be using smaller resistors and I would tuck it in between the two parts and make the board really as small as possible. But not today. Because, you know, we want to build these things by hand. One of the other things that we can do here is we see the reference designator for R2 is kind of underneath our USB connector. If we mouse over that reference and we hit the M key, it will allow us to move it. So, and keep in mind, everything that's in that teal color on the screen right now will get printed on the board. So it's kind of important to us that we put them in such a way that it's human readable, unless we elect not to print it on the board, which is common. But it's something that we have to go through and say, don't put it on the board. But for right now, I'm just going to kind of stick them out of the way. And R for rotate still works. Get those out of the way. And so now we have to deal with C1, C2, and C3. That's the one. So we can see that C1 and C2. So when you do a decoupling capacitor, you want those capacitors to be nearest the thing consuming power. In our design, what is consuming power? Yes. So C1, C2, and C3, we want to be as close to the FTDI as possible. Again, within reason. The reason is the resistance of the wire plus the capacitance of that capacitor creates a filter. It filters noise. There's an EV blog video on this that's really, really cool. I'll show it to you guys in a minute, later, after. Basically, when this chip needs to do something, say it needs to load data or it needs to mess with the differential pair, it needs to do something. It's going to take a tiny gulp of current. That's going to create noise. It's going to create a change in the output voltage of your regulator. And the filter that these filter or decoupling capacitors create will essentially mute that noise. It will completely destroy uh, the 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 noise that's generated by that tiny little gulp of current. It's think of like an audio low pass filter, right? You want to pass everything below 10 kilohertz. This is literally that, except instead of audio, it's like it's the electrical noise, and it's kind of in this situation when you think about a resistor and a capacitor being a simple filter that you kind of just get your toe in the water of what it is that, like, the math and the physics behind RF. Anyways, so these capacitors filter noise. Without them, this chip in operation could potentially affect its own voltage, the voltage that it's getting from the USB port. It could potentially affect that in such a way that it shuts itself off spuriously. If it takes a big enough gulp of current and the spike on that voltage is low enough, just shuts off completely, dead. So if you ever have a design where you have things randomly not working, things not working at all, take a look at your decoupling capacitors. Are they as nearby as they could be? Check the data sheet. In this case, our data sheet had a recommended size for all of our capacitors. Pretty much all microcontroller data sheets, all data sheets for basically everything will say, this is the decoupling that you need. But you also know the frequencies of the devices running in your system. For instance, we know that the USB clock is 48 megahertz. We know that from the data sheet of this chip. We know that the internal clock of this is 12 megahertz. We know what the frequencies are that we're dealing with. We know what frequencies we have to filter. Does that make sense? So if 48 megahertz is one of the fundamental frequencies of our design, we need to create a filter that will remove that 48 megahertz noise. And if you look at the filtering that, say, 100 nanofarad capacitor, the range, it will look like this if you chart voltage versus time, I think. Noise? Or no, it's frequency versus voltage. So the attenuation of the signal, how much of the noise is dampened by the filter, it will look like this. And you'll have a center frequency. And so you size your decoupling capacitors accordingly. So if you know, for instance, if you put like a 200 megahertz microcontroller on the back of this thing, then you know that your microcontroller needs to have a filter capable of removing 200 megahertz. Does that make sense? You know what's in your design. The manufacturer of the chip is going to give you some recommendations, but you know that you may need to go above and beyond based on the other things in your design. Potentially. Because like I said, if you look at those capacitors and you chart the voltage versus frequency, it looks like this. So if you go too low, it's not going to cut enough. That's why we use multiple capacitors. So what that will do is you'll get multiple V's in your chart. You'll have multiple centers. And what that allows you to do is effectively extend that window. So you have something that looks like this now looks more like this. And you'll maybe have some notches in there, but the more capacitors you use, the wider the window gets. That's why we have two very different values. So we have a 100 nanofarads, quite tiny, and a 4.7 microfarad. There's like 3 or 4 orders of magnitude difference in those two sizes. Right, it's got a window of filtering. So, now that we've got that out of the way, let's go ahead and place these components. So C3 is the is the capacitor for our 3.3 volt output. And so in that case, the consumer of power, if we look back at our schematic, the 3.3 volt out pin is the generation of power, and the VCCIO pin is where the power is actually being consumed. So what we need to do is we need to get C3 as close to pin 4 as is generally possible. But you have to keep in mind, you need to get a soldering iron in here. You need to be able to solder the pins on the chip, which are 0.65 millimeters apart. So I would say at least a millimeter, if not 2 or 3. You know, like if you have a 3 millimeter chisel tip on your Hacko, you know, you need to include at least 3 millimeters because then you can actually get your tip in there, right? So yeah, you kind of have to think in terms of human units and not just in KiCad units, because in KiCad, you can butt it right up. As long as your courtyards don't cross, it's not going to throw an error. It's not going to say, hey, you idiot, you have a 5 millimeter chisel tip. There's no way you can solder this. So you have to constantly be thinking not only what's possible in KiCad, but what's physically possible.
Can you tell it to just expand all the courtyards?
I,
Give it a setting?
I don't believe so, no. I'm pretty sure that those courtyards are drawn just like the pads are. The size, the orientation of all that of the pads. There might be a way to set the thickness of the courtyard line itself so that you get more area outside the part, but I'm not aware of a way to do that. And unfortunately, Googling things for KiCad issues is kind of a minefield because being an open source project, the goalpost moves a lot. And so the features that they have today may change drastically tomorrow. So the answers that you will get will become out of date quick. So if I had a recommendation for anyone searching for issues with KiCad, it would be limit to the past 6 months or the past year. Anything beyond that is probably going to be horribly out of date. Fun. So we know that pin 4 is VCCIO, and that's what we want to connect this C3 to. So if we look at the two pin names, we can see one's ground, one's 3.3 volts. So I'm just going to put this probably right about there. And if our grid spacing is 0.25 millimeters, well, I guess it's 0.1 now, but that's about a millimeter. I would say I could solder that, but you know, you may not be able to. So, you know, you kind of got to guess and gauge. What a lot of people like to do is they'll create a symbol, not a symbol, a footprint of their actual soldering iron. So they'll measure it out and they'll do it, and then that way they can move it around their board, and they could say, yes, I can fit my soldering iron in this area. This gap is fine. And it's one of those things that even if you leave it on the board, it's on a layer like the fab layer that is not displayed on the board. But so anyways, you can see that the 3.3 volt pad is lined up with pin 4 so that we can just sneak a piece of copper right straight out. I would say that is close enough. Could you get closer? Could you use a smaller part? Could you make it like literally touching the pin? Sure. Would it help? Maybe. At this frequency? No. Yeah. So if you've ever taken an Intel CPU and you've pulled it out of the socket and looked at it on the bottom, you see a bunch of capacitors. Those are physically on the die. They need to be that close because we're operating at such high frequency. When when you're in gigahertz, picoseconds matter. We're talking like 10 to the minus like 12 or 15 or something like that. So the other thing that we can do is we can connect up C1 and C2. So we can see that C1 and C2 connected to our chip is pin 20. So let's go back to what's up. Yes. Um. I believe that is either drawn by the person that did the schematic or those are actual pin functions. You guys don't have to do this, but I will properties edit with library editor. So let's see if they're actually, yeah, those are drawn by, oh, I guess not. Let's see, edit. So, yeah, so you can set pin function. So electrical type, we know it's an output, and they just said graphic style that it's an active low output. So that is indicative of its function as a pin, and I would assume that the other ones, like this CTS, would be, oh, it's an input. Let's see, output. Um, yeah. I would say that this is not the normal way to do it. The person, I mean, it is obviously the KiCad way of doing it, but the proper way of doing it is you see over here reset with a bar with an overbar. If it were me when I did this schematic symbol when I did it, all of these that have triangles would have an overbar. Anything that's active low would have an overbar. That's just how I would do it. That now the normal way of doing things and the KiCadian way of doing things are often different because people like to push boundaries, and sometimes the KiCadian way is better, and sometimes it's like what's with the triangles. But now we know. All right. Now, you might be asking, if we have our 3.3 volt output and we have a device out there consuming power, would we put a decoupling capacitor on that? And the answer is yeah, probably. But I'm not going to. Not right now. Theoretically, the only three pins that you need for this to work is you need to have a ground reference because these aren't differential signals. You need to know when it's high and when it's low, otherwise it's low voltage. It's just like having an earth reference in your house. Not quite, not really, but you get a circle that allows current to flow. It's like if you have a multimeter, you have to have the positive and the negative. If you don't have a ground, you don't have a voltage. There's no path. You have to have your ground, and then you have to have your signal, whether it's receive or transmit. The 3.3 volts out there is really, it's there for a utility purpose. If like maybe you need to power an LED or something, because I think the internal regulator for this thing is only good for like 30 milliamps or maybe 50 milliamps, and you drive an LED with 20. So I broke it out because you wouldn't really actually drive anything with that. Like if you were to connect this to your switch, you wouldn't be powering your switch from this. it's a communication thing. It's not a power thing. So I put it there because I knew that the 4-pin connector would be about as wide as the USB-C connector, and that even numbers are often more pleasant to the eye. We could have just as easily done 2 ground pins. Anyways, if I were designing a device that were supposed to power a target and communicate with the target, I would A, use an external regulator, and B, decouple the output, even though I said where power is being consumed. If you look at a board as a single unit, power is being consumed from that point. So, anyways. I won't be including one there, but you probably should. Just like you probably should use transient voltage suppression and filtering and lots of other things. So these need to be connected to pin 20. We see there, we have our fly wire. We have one to ground and one to pin 20. And actually what I'm going to do, I'm going to rotate it so it's facing up like that. And then we can get 2 components next to each other that are still quite close to what they need to connect to. Something like that. And then we can move J2 off into the back like that. And now it's just a matter of going through and wiring the quote unquote less important signals. Like the differential pair by far and away would be the most important part of this board, because if that doesn't work, nothing will work. And it's the one thing that specifically has specific requirements. Everything else can kind of just go and do its own thing, because everything else is much, much slower than the USB. So I will go ahead and start routing this. I'm going to start with the CC pins. Come on. And you'll notice that I sometimes fight with the auto router, like I am currently. Why are you doing this to me?
The auto router, like when going in and out of chips, it seems a lot more okay with right angles.
Yeah.
And
There's
the quirk of the auto router.
there's an aggressiveness, an optimization aggressiveness setting that you can twiddle with and mess with, or you could disable it altogether. I sometimes can not make heads or tails of what the hell it's trying to do. But when you've been working with it for a few hours, like contiguously, and you've learned that, okay, it does have a mind of its own, but now I kind of understand that mind. So you get, there's a little bit of intuition that you build up with it. But the problem is that often it's different every time you open the application. Just doing the power there. And the power here. Now, these are skinnier tracks than I would probably normally use, but we're not talking about a whole lot of power here. Later on, I will link you guys to a piece of software that is incredibly useful and will shotgun information at your face. So, basically, it's a calculator for everything electronics, from like thermal dissipation of a trace that's this size to the impedance characteristics of a piece of fiberglass that's this dimension and has copper on it of this dimension, like microstrips. Like it goes from 0 to 60 real quick. It's like it's just a window that's got tabs, and there's about 30 tabs. It's got a lot of information, and it's helpful to pretty much anyone doing anything electronics. I think like the only thing it doesn't have is maybe like Ohm's law,
Wait,
but
what?
but because Ohm's law is so easy to remember. Let's do transmit and receive next. What I'm going to do is I'm going to put a little bit of extra clearance on the USB traces, because the closer you get to those, the more noise you're going to couple onto those. What's that? So the closer that we get to this differential pair, the more noise we'll couple onto that. Yeah, ideally. I mean, within reason. Again, the clearance on this USB, if we're talking like a millimeter, millimeter and a half, anything more than that is enough. But even then, like, we're still talking like 115 kilohertz max on these transmit receive pins. So, it might be an exercise in futility, but if you exercise that now rather than when you're working on a board that's a couple hundred megahertz and you're scratching your head trying to figure out what the hell's going on, you build that behavior now when it doesn't really matter. That way it's already built in by the time it does matter. So you can see that I've routed these transmit and receive pins as close as possible as I could, literally. Because although they will couple noise onto each other, it will be a magnitude that won't matter to a UART, because the timing is not strict at all. The other thing that you'll notice is that I haven't been connecting any of these grounds. Ground, 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 all those things not connected. There's a good reason. If you've ever looked at a circuit board and you see a big copper area, it's the same thing we're going to do, and that's pretty much always your ground. You want a low impedance on your ground. And now I said before that impedance is kind of out of scope for this, but I'm gonna try and explain it in a way that can be understood that won't take 2 years. It's a way of thinking about restriction of flow of current. If the loop that your current has to take is small, like if you remember when we were doing this, we got that as small as we physically could. The loop is small, the impedance is low. The bigger that, like if I took this loop and made it a big old antenna underneath the USB cable, the impedance would be high because the loop that it travels in is quite large. Does that make sense? So if I was drawing current out of this 3.3 volt pin from this chip, but the ground had to go all the way around here to get to there, you would have a big antenna. You would have, the impedance would be high. In order to get a as low impedance connection as possible, what we would do is plate both sides of the board with a ground signal and lots of connecting vias, so that a current has the shortest loop possible. Loop area is super, super important. Does that make sense? I mean, you can have a signal that goes from one end of a giant board to the other, and that's fine. That might be necessary. But you want the ground that travels along with that signal to be as close to that signal as possible. So if you have a signal that goes a couple millimeters and its ground has to go around the board, that's really bad. You have a big antenna. So that antenna is going to pick up all kinds of external noise from other signals, from exactly. That ground is your reference. I mean, it's the same if you have a short ground and a really long signal. It's basically the same. The signal becomes the antenna. You're going to couple all kinds of noise, and you don't know whether that signal is actually moving or it's just a lot of noise. So basically, the easiest way to accomplish what I'm describing is the best way to do it is you have a multi-layer board, like say a 4-layer board, and then you dedicate one full entire layer to ground. And that way, regardless of where your signal goes, it has a plane of ground that can follow it. Another good way to do this is to do a 2-layer board and devote the top layer to signals and the bottom layer to ground with lots of through vias, so that the ground pins on your parts can connect through to the plane. And that's what we're going to do. Actually, what we're going to do first is we're going to actually draw the shape of the board, because right now this is just a bunch of parts floating in space. There's no board to go around it. So what I've done is, if you see the blue arrow, I've selected the edge cuts layer on the right over here. It's that yellow one. I've just clicked it. And what that does is that says I want to draw on the edge cuts layer. And then this here that looks like 4 lines with dots, it says add graphic lines. We're going to do that. And then when we draw, we're going to get a yellow line. Now, what I like to do when I draw circuit board outlines, I like to go maybe like a 0.5 millimeter on my grid spacing. And that will kind of allow me to give a couple millimeters extra in any direction. Like I know the edge of my circuit board needs to essentially be there. There are other tools which you could draw like a box in, but not KiCad for reasons. KiCad doesn't want its users to be put into a box. So all I'm going to do is draw a bounding box and envision this as the physical, I screwed up, the physical dimensions of your circuit board. So if you have something like this, like I have on my screen, that has that jag off the edge, you're going to get that in your board. So what I'm going to do is zoom in a bunch because these lines are skinny. And then you get like the white dot at the end. You can't really see it, but it'll give you like the little grip. And then you can go down. And then same with that. And so now I have an outline. And if I were doing this, I would probably move C1 and C2 so that they're like that, so that the board is like equal. Right now it's kind of like a bit tall. Anyways, half of it's about making it look nice, which I'm kind of not really going to do. So we want to do our pour. So over to the right on our tools, there's this button called Add Filled Zones. And it looks kind of like a track with a via with copper around it. Copper pour, that's a filled zone. That's our big area we're going to fill with ground. So what I like to do is then outside of this drawing for our circuit board, once we click, oh, actually, I lied. Before we do that, we're going to switch to front copper. And then we're going to do that. And now it's going to pick us. Now it wants us to pick what net it's connected to. In this case, we just want a ground plane. In other cases, if you wanted to do like a big thermal mass area for like a power regulator, and you wanted to like bring that to the other side of the board where you have a heatsink soldered down, there's various reasons why you would want to make a plane, but in this case, we just want a ground. So, and KiCad kind of knows that, and it says, oh, I'll put the ground at the top. So when you do that, we get this line, and then we get to draw another box. And it kind of as you draw, you can't really see it on the projector, but everything inside that triangle that I've drawn so far is tinted red. It's going to be easier to see on your screen. And then as I do this, see, it's a little bit easier to see once I finish it, I'm sure. And then, so when you want to place the last point, double click. And then you can see Now that's all filled in. Now,
Is that for front copper? No, that's for back copper.
that's for, well, actually, what I'm going to do is I'm going to show you another cool feature. Since we know that we want ground on the front and the back, and we've just drawn this, let's go back and hit E, and let's just tick front and, oh, will it not let you? It used to let you. I lied. Another box. You used to be able to do both, but apparently not anymore. So we're just going to do the same thing, and all I do is I do one grid spacing out. That way it's easier for you to see each layer. The yellow line is the physical edge of the circuit board. I wouldn't know. I'll have to take your word for it. Did it not do what I told it to do? Yeah. So when I do that, it's gonna, yeah, it'll show up green. So now you get this sort of hatched area so that you can mouse over it and hit E and edit it and do whatever you want to do. I typically don't make it identical to the size of the plane I actually want, because a KiCad is smart enough to go, oh, that's the edge of your circuit board. You don't want a plane outside the edge of your circuit board. It's kind of intelligent in that way. And you can see that where there's green but no red, but there's these tracks here, that's the default clearance. So if I go back into my plane here, you can see clearance, minimum width, thermal distance, thermal spoke. So the thermal spoke is, if we look at this pad that has this sort of T shape inside of it, those are called thermals. So if you were to solidly connect that pad to ground, it would sink a lot of heat. It would be difficult to solder. So KiCad by default will do thermal reliefs. That means it's connected with a very low impedance connection, but it's done in such a way that it's not going to draw a lot of heat out, so you're not heating up your entire circuit board just to solder your connector. The spoke width is actually the width of the T. So the cross and the bottom. If I were to increase that, those sections would get wider. The thermal clearance is the actual ring where there's no pore. You could make that bigger or smaller. I usually like to stick with the default values unless I'm working with a chip that has pins that are extremely close together. Most fab houses can do what's called a 6-on-6, which means, and again, it's in inches. You have a 6 mil on 6 mil clearance, which means the distance between your pads can be 6 mils. The distance between traces, basically, the distance from any section of copper to any other section of copper can be 6 mils, or 6 thou, which is pretty good to do anything. I think I would be surprised if we got lower than 8 here, although that USB connector is pretty close, so it's going to be kind of tight. And then the clearance is obviously the overall clearance on all of your wires, and the minimum width. If it had to sneak a section of copper between two other sections of copper, that tells you what the minimum bit of plane would have to be, basically. You know what I'm saying? And then we could do solid. I don't actually know if that's going to change anything. Yeah, so see, now it's like hard connected to that pad. There is no more T. It's just copper all the way. If you wanted a really, really high power connection, that would get the job done, but it would also make it almost impossible to solder. Like if you've ever tried to solder on like a PC motherboard, like a proper computer motherboard, it's a giant pain in the butt. It's because those things have like 10, 16 layers. they've got thermal reliefs, but there's so many ground planes that it just pulls the heat right out. And that's effectively this. Crazy, isn't it?
There are few areas where it doesn't seem to go to ground. Well, no, you've got it too.
Yes. That's because the clearance issues are technically violating the default setup. Like if we were to run the design rule checker right now, which basically goes through and verifies that if I go through, that's what this bug thing is. There's a design rule checker for the schematic and for the board. If I click that, it's going to give us just a mountain of issues. If I hit run DRC, oh, it wants me to refill. Yes. Or maybe it'll come up with nothing. You never know. It's a hat toss.
Well, but it looks just like, from looking at it, it looks like the side ground of the USB-C isn't connected to anything.
It's not, because if you look between the two, there is actually a gap between those pads, and you actually have to connect it because we've told our plane that our minimum width is 0.254. What I would normally do is what I'm going to do here in a second, and that is just draw a piece of copper, and that. Yeah, what I would actually do is I would draw a little mini copper fill that has a much thinner minimum width, or I would have it solid connect, but not cover the whole pad.
Yeah.
You know what I mean? So it would like solid connect that pad to the very corner of the other pad. You know what I mean? So you would still kind of have a thermal relief, but also have a really low impedance connection. And there's kind of little things that you can do, little tweaks, because you don't want your global fill to have a really narrow clearance, because then you might end up in situations where you don't actually want a clearance that low. So you just do little mini fills for various areas. Let's see. So we need to connect all of our 3.3 volts together. We need to connect this ground together because the clearances are such that it's not connecting. So we're going to throw a via in there. And of course it's going to do that because I've switched to that layer. So one of the things that we have control over here, if we look at this, it looks like the same button over there, but it says show filled areas in zones, don't show, or show outlined. So this is kind of cool in that it only shows you the boundary of where your planes are. That way it won't do what it just did and illuminate my entire screen green. So it gives you some idea of where everything needs to be without blinding you. I'm also going to lower my grid spacing again. Just going to throw up. Well, you can always move things around. The other thing I'm going to do is this yellow dot tool over here, the add vias tool. If you put this down on a signal or a plane, KiCad is smart enough to say, oh, I will just make that via go to that signal. So if we drop this in the center of this ground plane, it goes, oh, look, it's just a ground. Have a ground. Other tools, not so smart. You got to put it down, you got to name it, you got to put it down, you got to name it, you got to copy it. Bit of a pain in the neck. But KiCad, in this respect, is a bit easier. So what I'm going to do is, along this USB track, I'm going to try and get as many of these things as I can within reason. And in some ways, much like the shield on a USB cable will help reject common mode noise, this ring of vias will encapsulate those signals, because now you have ground surrounding those signals. And the spacing of these vias is dependent on the frequency, the wavelength of that frequency. So you basically you want the if you calculate the quarter wavelength of your frequency, the distance between your vias needs to be equal to or less than that. It's a lot of vias. But we're only talking about 48 megahertz. It's something like 4 millimeters or something. It's almost not necessary for this, but it's good practice. So, in a USB cable, you have a shield. You have a braided cable that goes around a shield that's connected to ground at some point. Adding the vias does essentially the same thing. You have this microstrip that's going across one side, and now you have ground that's covering 3 sides of that microstrip. The distance that your vias are placed is dependent on the quarter wavelength of the frequency that your pairs are operating at. If you calculate that for 48 megahertz, it's something like 3 or 4 millimeters. It's almost not necessary because your board's not even that thick. You know what I mean? I'm throwing him in here because it's good practice, and it also helps you space everything out so you know that this is where my USB is, this is where other signals shouldn't go. You know what I'm saying? So
Mine like doesn't have as much space as yours to put things, so it's like
I believe if you hold shift it will stop snapping. Or maybe it's control. Alt? Huh. Weird.
oh wait, that did something a little different.
Oh yeah, if you adjust the spacing of your grid, that will allow you to get closer to the trace without it snapping. Mhm. Yeah, for routing, I have mine set to 0.1, not 0.01. Yeah. So that's actually why I don't really like this view. I usually opt for the off and then just assume that anything without a rat's nest or an air wire, the rat's nest is composed of air wires, so each one of these gold colored wires is an air wire. Anything that doesn't have an air wire is connected by a plane, is the assumption. And then during review, what I'll do is I'll turn this visualization back on and look for big open gaps or orphan sections which aren't connected to the main plane. And you would get air wires if you did that, but this still looks pretty good. Except for where, yeah, that's correct, yes, currently. But that's potentially subject to change. But the other thing is that, yes. Now, keep in mind, not necessarily required for what we're doing, but building good habit, good design starts from the beginning. So if we were to look at the planes here, you would notice that the wire that I just routed goes through a section of plane that exists. So there's a shortcut to repour the plane. I believe you can right click or maybe go to tools. Well, anyways, it's B. You just hit B and it will repour. That's the nomenclature. And so now you see this here. This is a good reason why it's good to often look at the planes with them visible. This ground here in the center is what's called orphaned. It's not actually connected to anything. If it weren't for this via here, it would be connected to nothing. So in this case, what I would actually do is delete that section and move these over so that now there's plenty of room for that ground to sneak through. There is an actual difference in doing that electrically beyond the capacitors themselves. You know what I'm saying? So now our ground is actually connected. It's connected to these capacitors all as well. You always want to, while you're routing, you can turn the visibility on and off of your planes, but you want to consider the path that all of your signals are going to be taking. And that includes the signal itself, but also the ground for that signal. So if I look at bottom copper and there was a big trace running through the middle of the board that was going to affect the way one of my signals goes, like the ground connection would have to go around that wire, you might want to reconsider your placement of that. Maybe go around the edge of the board. You know what I'm saying? So it's all, yeah. I mean, like this design, it's pretty much going to work no matter what you do to it. But it's that building the, best practices. You got to start early. If you don't, things aren't going to go too well. Well, we've got to connect them. We haven't gotten that far yet. So what I'm going to do is I'm going to just turn this back off real quick. And then we'll notice that a lot of these kind of connect to the same point here. I think tilde, if you click tilde, that will show. It's also this button here, it looks like, highlight net. So it allows you to pick an air wire and see everything it's connected to. So all of these pads kind of connect back to a single point. So what I'm actually going to do is tilde. Yeah, you got to click something like a pad. There you go. I'm actually going to create another plane because what this signal actually is the 5 volts from the USB connector. So I'm going to underneath our connector, I'm going to put kind of a large plane that all of these things can go back and connect to. It's not strictly necessary. And squeaking a trace out of there isn't really going to be too easy. But I think even with our default clearances, see, it wanted to route those two completely differently. Okay, get those out. And then I'm just going to drop a plane in there of arbitrary dimension. And we're going to name it whatever it wants. In this case, it's net C1 pad 1. It may be different for you. Just going to draw it like so. Come on. Now, since we have overlapping pads, if I display them and re-pour, we see no plane because they're overlapping. There's no, currently, the precedence for those planes is not set. So I can never remember precisely how it works, but I think if we go to our new pad, which is connected to not ground, we see this zone priority level. If we increase that to 1, hit OK, now we have our zone. So the higher the priority level of that zone is what the precedence of when it gets poured. Do you get what I'm saying? So now what we can do is we can bring these signals back and connect to sometimes I swear the autorouter really does have a mind of its own. We've got those connected, then we can get these capacitors up here connected. And then what I'm going to do is I'm just going to add a couple more vias just to make sure that ground can flow from one corner of the board to the other unobstructed as much as possible on both layers. You see where I'm getting at? It's all just kind of, so like in here in the center, this sort of rectangular section, I kind of hit every single corner with a via. That means that even if power were to start from that top right corner and absolute worst case scenario need to go to the other bottom right corner from the top layer, because that's where all of our signals are, it can jump to the bottom as soon as possible. From any point on the board, if you pick a point and need to go to another point, the position to drop to the bottom and get over to that point needs to be as short as you can get. I mean, within reason.
The large plane on the bottom side is also ground?
Correct.
So I'm sorry, I missed the part where you were setting the priority.
Yes.
Make it the oscillator. Okay. So that just, you want it to be a little bit higher than the ground plane?
Yeah, it doesn't really matter what it is as long as it's higher than 0. Because you'll always have your main planes set to 0. Anything with a higher priority gets a higher precedence. And I've only got one trace left to run. I think I'm going to go on the bottom. So this is one of the cases where you could really shoot yourself in the foot. Because there's a bunch of different ways I can route this signal. If I, sort of start here and then go up along, I need to do that. Drop to the bottom. I can route it like this, and it'll let me. But that's a giant foot gun. Why? Because it's running directly under our USB. It's cutting that ground plane almost in the middle. It's causing all kinds of problems. So what we really want to do is go along the bottom edge as much as we can, kind of try to avoid as much as we can. So what that's going to do is it's going to cause a problem here with this ground, but we can add a bunch of vias, and it will essentially bypass that signal as if it weren't even there. Now, again, you might say, why are we going to allow the TX and RX pins to cross a ground plane when that should be verboten? Well, the answer is because they're really, 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 really extremely slow. And I'm done. Ground on J2 is connected, and I did repour. See, well, I guess I should probably move this one. J2 is connected to both the top and the bottom. So even without all these vias, we would see if I switch over to the top, we have this ground connection coming through here. I mean, it's an ugly loop and it goes quite a far distance. But that's where our vias come in here. This little jump here allows any current coming from this direction to quickly jump to the top of the board and directly to that ground pin. So that the loop is still very short. If we didn't have either of these vias, any current, not hit the right button, any current that had to come this direction would be completely cut off. Like it couldn't even get around this trace. But because these vias are here, that gives that power a way to sneak through. This is maybe not the best way to do it. Like we could extend the board out another millimeter or two and then sneak that trace behind this connector. That may possibly be the best way to do this, but I'm too lazy, frankly. What do you mean? Yeah, so these yellow pins, the there's no real difference between a via and a pad. They both do the same thing. They're both plated through holes. It's just like logically, I know that one is part of a connector. Like these 4 pins are apart. They are, not just some floating hole in the board that's going to connect 2 layers. You know what I mean? I mean, they do that, but they're logically separate. So, yes, in much higher current too, you'll find that the bigger the diameter of your via, the more current and more heat it will carry because there's more copper. That's why a lot of times if you find a thermal via that's like underneath a big MOSFET, there'll be big holes because they'll carry more current, more heat. So what I'm going to do is one of the coolest parts about KiCad, and I'm going to hit Alt-3. There's also a menu shortcut for it, but keys being what they are, the majority of the parts in the KiCad library have 3D shapes. It's one of the reasons why it's 5.3 gigabytes. Now, this is a relatively simple board, and my solder mask is dark, so it's difficult to see up on the screen. So I'm going to change my solder mask to, let's go with light blue. And you can see all of our traces, our planes, most of our objects. The USB-C connector doesn't have a 3D shape. But yeah, this is a great tool. If you can export this 3D model to your favorite 3D modeling tool, 3ds Max, whatever you want, Inventor. If you're, say, designing an enclosure for your product and you want to make sure that that enclosure doesn't foul on a big capacitor, a connector, what have you, you can directly import it, textures and all. It's really cool. Possibly the most powerful part of KiCad, aside from the library, I would say. The other cool thing is, if you go to DigiKey and you say, oh, this part is perfect for my project, but KiCad doesn't have it. A lot of times what you can do is you can go to DigiKey, and DigiKey will actually have the 3D model for the part. So you do your symbol, you do your footprint, and you just go, oh, look, they got a model, cool. A lot of times it works out like that. I mean, in KiCad, what you can do is when let's say we pick this IC and I hit edit. If you look, there's a couple tabs that come up, and one of them is the 3D settings tab, and it'll actually render that part in a window. What you can do is you can mess with the scale. So say I want to mess around and make the X scale 0.5, make it one thin boy. Now I go back to Alt 3 and I re-render. We have one small boy. So, say if for some reason you don't want to draw a 3D shape and there isn't one available and you just want it to look the right size on your board, you could take a similar like a QFN quad flat pack no lead that has no legs on it. You won't be able to see the legs, but you want it to be the right size just so it looks right. Drop in the wrong part, but scale it so that it looks right. It's the right dimensions for that part. It's good enough for me. So it's pretty powerful. I like it. And if you'll notice, in this entire time, not one of us has had KiCad crash on them, and it's been 3.5 hours. I can tell you from experience that it has not always been this way. It used to be once every 10 minutes or so. I've had it crash on me a couple times, and I have lost a couple hours of work, and you really need to get on that Control S action anytime you do anything, because losing work sucks. It depends. If it's something like this, a small one-off project I can do in 5 minutes, probably use Eagle. Actually, I don't have Eagle installed on this computer, so I guess maybe I am a convert.
You're a complete convert. You made it.
I guess it's not perfect. I still really, really like Eagle. Like, really love how small and simple and easy it is. No. I mean CADSoft Eagle, not Autodesk. Get that out of here. CADSoft Eagle is a 56 megabyte executable, and that's it. You get no kitchen sink, you get no kitchen. Anyways. It's like a mansion, but half of it's falling over. I mean, there's kitchen sinks, not necessarily in kitchens.
We have a kitchen sink in every room.
Yes. Why is there a kitchen sink in my bedroom? Yeah, so the user experience is not quite there yet, but it's making leaps and bounds. Over even like the past year, the library has grown like immensely. The download size doesn't actually change all that much because, like I was saying, I said before, they like to optimize the libraries. So they'll either redraw, because a lot of times when you get a 3D model from a vendor, it'll be a gigantic file for no reason. So a lot of times they'll go through and they'll either cull duplicate models or redraw them in a format that is, not precise down to the micron. Because a lot of times what the manufacturers will do is they'll actually give you like a 3D scan, like a point cloud 3D scan converted to an STL, and it's just a gigantic file, like for no reason at all. So, yeah.
Are they like good 3D scans or?
It's a 3D scan point cloud converted to an STL.
So the answer is no. Okay.
If that doesn't give you some kind of disease just hearing the description, I don't know what will.
Conversion sounds terrible, but is it like a 3D scan where this would have a random snake through it because something was reflected off of it?
Yeah, I mean, basically, yeah. A 3D scan is a sort of thing where you can use it, the technology exists, and you could 3D scan your face, but you would spend 8 hours fixing all of the little rips and tears in reality.
Yeah, okay.
And while their converters attempt to do that intelligently, it's just that's
One of the biggest parts of it, which is why it is so wasteful, is that even if you are using a converter, it's not necessarily able to determine like, oh, I've got like points here, and here, and actually determine, oh, that's actually just like could be one fucking quad.
Yeah, could be one quad, and we're talking like a speck of dust caused you to create 1,000 polygons essentially, because the 3D scan was that precise. Okay, so let's go ahead and let's do that step. And to be honest, I always Google this step because while I might remember, I don't need to give myself another opportunity to footgun myself. And it's documented flawlessly. Why wouldn't I? So let's do it. Let's open up the browser window again here. And there is a US fab that I really, really love, and I really, really would love to work with them on every project, but they're about 5 times as expensive as China is, even with DHL shipping. And that company is Oshpark. They have Perfect Purple PCB, and I think they call it Midnight Black, which is clear solder mask with black FR4. They also do flex, but flex is like $15 a square inch. It's spendy. Yeah, it's a. So you know the flat flex cables that you commonly find in laptops, and sometimes in displays you have like a flat flex connector that has like components on it. That, yeah, that's the kind of thing that you can get fabricated. Nope. No, so their JDEC is the like one of the standards bodies for electronics components, and for all of the packages there's a JDEC package, but there is also a JDEC package stress section where it's spelled JEDEC. You've probably seen it somewhere. They outline exactly how you should lay out a connector based on how its substrate is going to be bent, and the most optimal way of doing that.
But you probably want to use the smallest sized components you can.
That is correct.
So that's when you start using the right grain resistors.
This guy built an LED cube with the flex board. Yep. There's also a company called, I think, Harman Instruments. They they they've done a lot of really cool RF stuff, and one of the things that they've done is filters, a series of filters with the board. So let me actually just go off on a tangent really quick, because I think it's cool as hell. Let's see if I can get a good image. It's not really the right keywords. Let's see. Yeah, here we go. So like what we see here, these traces are physically not connected, and yet RF will pass over them as if they weren't there. I mean, not as if they weren't there, but what you're actually seeing here is a series of capacitor plates. Yes. It's actually using the air between, well, the circuit board and the air between the sections of gold-plated copper as a dielectric. The signal is actually passing through the circuit board and the air between the plates of metal, almost as if it weren't there. So the PCB that we're seeing here, you can actually see is white between everything. That's actually a ceramic substrate. The precision with which these circuit boards is manufactured is like orders of magnitude better than discrete components. It's cheap. It's free, essentially. I mean, you've got a board that's got to be that big. You might as well put it there. Not only are we talking very precise, but very minute. The parasitic inductance and capacitance involved in having a physical component is actually huge when we're talking about like 10 gigahertz. So the capacitance of these discrete filters is quite small. There are other filters, like if we look at this.
Let me see if I can understand this. You couldn't get a capacitor small enough to be able to filter out what you're getting there
Correct.
by actually having the correct spacing between.
Correct. The physical dimensions of the capacitor itself, because it's a brick essentially, and it's soldered on, and you have that blob of solder. All of that has a physical effect because of its size, because of its shape. You physically could not, I mean, both in terms of size, but also in terms of value, the capacitance. Yeah. Yeah. So this is another form of filter. So the long straight parts are inductors, and the bricks, I guess you could call them, are capacitors. I mean, they're also inductors, but they're mainly capacitors. So the inductance of a section of wire can be measured. And when we're talking about frequencies of this range, values that are that small actually matter. They actually have a very tangible effect on the signal at hand. RF is just like, this is another form of capacitor, and the little squiggles, again, inductors. Yeah, so everything that we're seeing is a series of high pass, low pass, and band pass filters. That's all it is. It's a filter. It's insane. And it's all based on essentially physics at this point. We're talking about reflections of current, parallel plate capacitor physics, and inductance. It's all like, we're talking down in the electrons essentially. RF is just insane. Correct. It's intense, but there are a lot of calculators to help you. Like, there are software just like KiCad where you can say, I need a discrete filter of this specification at this frequency range, and it says, okay, and spits it out. Yeah, there are these tools that exist. I mean, like, there aren't engineers that are out there with napkins, like, doing all of this, differential equations and calculus to come up with everything they need. It's more or less done for them, but the software is immensely expensive. So anyways, they have FlexBoard. They also have the Midnight board, which, let me see.
Boards. So my first and only other experience with this, we made our own boards using Acid-X.
Yep.
Is that like something that's worth doing anymore?
It's possible. You have to be very, very specific about your procedure and how things actually get done. But I would say anything less than like 1 millimeter pin spacing is not really going to come out. Because what happens is, even if you use the 2-part UV reactive, like the pre-impregnated, what you do is you print out a mirrored copy, and then you put it down and you expose it to UV. Anything that's not exposed to UV gets hardened. You use your developer to remove that hardened resist. Then you let what's left harden. Then you etch the copper away. But what happens is, when you have features like that, the acid, so you have like, say, a rectangle, a box of copper that you're trying to not etch. So you want to etch everything out around that. And on top of that, you have that resist. What happens is, you're never going to etch perfectly around that. You start to get pitting, and what happens is it actually eats underneath your resist, so the pad will actually round over, and it will actually eat into that pad. So the physical dimensions with which you can get with that are quite limited. I know a guy on Twitter, a person on Twitter, who uses a CNC mill to mill circuit boards, and they've been able to get really, really good, really high precision out of that.
Reminds me of that weird Kickstarter project for a circuit board printer that used paste and
Yeah, I don't know about that.
it was
Anyways,
a very expensive way to make very cheap boards.
this is what the Oshpark black FRFR with the clear solder mask looks like. It's very retro looking. Like you can get some really cool Tron style stuff out of that. Looks super pretty. But the important thing is you can see all of their boards are ENIG, ENIG, which is electrolysis nickel immersion gold. So what they do is there's a process called electrolysis nickel, which you plate copper at room temperature without electricity. It's not electrolysis, it's electrolysis. It's a weird process. Anyways, it's about electronegativity. Huh?
Are they using gas sputtering?
I don't know how it works.
Stuff like that in a vacuum.
Anyways, it's all about electronegativity. You can't plate copper directly with gold because it's too much effort. You lose a lot of gold in the process. It burns as you try to plate it. So to bridge the gap, there's like a big chart, and copper's down here and gold's up there, or vice versa, I don't remember. In the middle is nickel. And the electrolysis process deposits a lot of nickel. We're still talking like microns of nickel, but you're only depositing about like a 1 atom wide bit of gold because it's not hard gold, it's plating. So what you're seeing in the picture here is the squares are gold plated, but you're actually seeing the copper through the clear solder mask. That's why there's a very, very small color change between the two. Now normally that would just be covered with your color, but it's clear.
Oh, that's scary ass shit. Do not do it at home.
Yeah.
It's not vacuum sputtering. It's just a very, very aggressive redox reaction.
Yeah, it's nasty stuff.
Yeah, so you're stripping the electrons off. You strip so many electrons off that the metal jumps on instead. Anything that can strip that effectively. Let's see, what was this one? It's sodium hypophosphate, which
Yummy.
think alien blood.
It has both sodium and phosphorus in it.
Yeah, well, that's not the problem. The problem is it's okay. You've heard of the pH scale, okay, and how it goes from 1 to 14. That's a lie. You can get negative numbers and above.
Mm-hmm.
The
Super acids.
down, okay, they don't actually make sense because you're not actually talking about hydrogen anymore.
Fluoroantimonic acid, am I right? That is the most powerful acid. It's like a minus 25 or something like that.
Well,
I mean, the scale breaks down, but it is effectively the strongest acid in the world.
You start talking about the actual electrons that are jumping
Yes.
rather than the hydrogen.
And basically what happens is fluoroantimonic acid, when it starts to react with something, you get lots of fluorine gas. And fluorine gas is one of the most reactive substances in the world. And so you have this reaction that's going on with the acid, but the fluorine gas essentially just catalyzes the entire thing. So it's just it's like think runaway reaction, like exponentially runaway. No. In fact, you can't really get it anywhere because there's almost no way to store it. It reacts violently with Teflon, which is, as you may know, one of the most unreactive substances known to man.
You can actually store it in steel, which is very strange.
Yes, the only reason why you can do that.
It's got a running reaction with the steel that cancels
Correct.
out what it would eat away.
So what it does is, if the barrel remains perfectly still, or almost motionless. It forms an atom-wide barrier of oxide, essentially, which is kept in constant flux. It's constantly being eaten and reformed. The moment that the acid flows across the steel, it has an opportunity to wash away that oxide. It immediately combusts. Yeah, there's lots of rocket fuels that are like this. Hydrazine was one of them until they developed Teflon and plastic containment.
And then there's foof, a
Foof.
chemical that is usually that has been described as evil in chemical form. It reacts with itself at above -200 centigrade.
Mm. The vapor pressure of it inside a barrel is something like 200 psi or something insane like that. So not only is it reactive with itself, but you have to let it constantly vent, otherwise it will physically rupture the container that it's in.
Well, foof, no, you don't contain. You make like a milliliter at once.
Yeah.
If you really need it.
Yeah.
And
Okay.
its
Okay.
primary purpose
Anyways.
is to make hexafluorouranium, which tells you a whole lot about
Yeah.
why it's made.
So, anyways, massive tangent, but Osh Park, they're awesome in a lot of ways, namely that they have KiCad fairly well documented. So, what I'm just going to do is I'm going to go KiCad export Gerber. And you'll see JLC, PCB, seed, Osh Park, KiCad, generating Gerbers. Normally I put Osh Park in there because I know exactly what I want. So it's going to tell you want to redraw your fills, even though KiCad now throws up a window that says, "Are you sure you want to do that? Maybe let's refill the fills." The ground plane. When you press B, yes, B is refill fills. You want to make sure you have a board outline, your edge cuts. We did that. That's the yellow line. Now we're actually gonna generate. We're going to do some rubber road meeting action. So let's just make sure we've saved, hit B, wait for it to do its thing, and then we're going to, this button here says plot. It's next to the printer. Okay. Now the window as it is now looks different from the one that's documented in Osh Park. But the gist is the same, and it does work. I have tried it. So we're gonna go back to Osh Park, and we want our silk, we want our mask, we want our copper, we want our edge cuts. Okay, so we'll go to PCB new, and we have copper, paste, silk, mask, and edge cuts. It's exactly what we want. It's exactly what we need. We want to make sure our plot format says Gerber. That's what it should default to. Not that. That. And then we want to... Usually all I do is just look at this. So we've got all of those layers. They don't plot paste, and it's not something you really have to worry about. Even if you did plot it and include it in the file and send it off, they're gonna ignore it. What that is that's a negative of your solder mask. Essentially, it's not quite, but it's where all your copper is, where you want to solder something down. So if you're gonna have a board manufactured and they have to silkscreen solder onto the board, they make a stainless steel stencil. This is the negative of your solder mask, so it tells them where to laser cut all the holes where all the solder goes. If you're not getting a board assembled, you don't need to create that layer, but it's like a 2-second thing, and it's on by default. So I always leave it on. What do you mean? Well, right. If you specifically want something to have solder on it, you would put it in the paste layer for manufacturing. But if you wanted like a pad that you could solder to, like a via, you can't solder to, because if we go and look at our 3D viewer, you can see that like this pad here is exposed. We can see the gold, and this one isn't. I mean, you can see a little ring of gold, but if we go to our PCB view, we can see that our vias are about the same size as that pad. They're tinted. There's no solder mask. So if I close, well, actually, let me go back to another good example is the holes for this connector. So if I go all the way and look at the bottom, you can see, and in fact you can see in here, there's a ring of brown around the copper. And that means that your solder mask expansion is slightly bigger than the pad, and that brown you're seeing is actually the core material of the board underneath the solder mask. Now, you may have seen, like, in a computer power supply, it's like a one-layer board, and it's just like a brown board, no solder mask. That's what that is. Same stuff. I mean, not precisely the same, but same, only different. Right. So when they if you send your boards off to be assembled and they have the surface mount components, they need to know where. So basically, what they have is they have a machine they load up with solder paste. It's like microscopic balls of solder suspended in flux. They essentially have a big machine that squeegees solder onto your board. So what they do is they take like a 3 mil either mylar or usually stainless steel stencil, and whatever's on your paste layer is what they cut. So if I go back into here, PCB new, and I close this and I look at the F paste layer, which is also red for dumb reasons. If I turn top off, everything that's red here is gonna have paste. So if for some reason I wanted to default not populate C1, I could go into C1, his pads. I probably have to turn top back on. I do that, and then I do this. I think there is a way to do what I want to do. Pad, edit. Yeah, here we go. So see how this has F paste on it? If I turn F paste off for that specific pad, and then I go back here, turn front copper off, and then select my F paste layer. Come on. See, now there's no red there. So if we were to get these boards manufactured and assembled, and we sent them this paste layer, this pad would have no solder on it. A lot of times, people like JLC PCB, they'll do that. You could say, I want boards, but throw in a $15 stencil. And in which case, you would need the paste layer anyways. So that's why I say, like, generate it now, because if you finalize this design, you say, you know, I only want to assemble 10 now, but, oh, you know, well, let's maybe do an Indiegogo and we'll sell a couple hundred. You don't want to have to then go back and modify your design to generate your paste and make sure everything's okay. It's just easier to do it and be done. Especially when in KiCad, let me just undo that. Especially when in KiCad you go into plot and it defaults on. You know what I mean? Now, there are some instances where, say, you want to mount like a AA battery holder to the back of a badge, and you want to by hand, you know, stick that on and solder it on. in that case, you wouldn't want a paste layer over that. You know what I mean? Because you're going to hand solder that with it. It'll probably be on the back of the board because you only want single-sided assembly. Double-sided assembly, like, triples the cost. You wouldn't put paste on that, so whenever you're drawing that pad, however you draw it, you just say exclude paste. And now you can see, so the purple that you can see around that is the solder mask expansion. That's the hole in the color. And the red is the paste. So that's why I say it's not quite the negative of your solder mask layer, but it pretty much is. Because that's like 0.01 of a millimeter difference. It's not really going to make a huge difference. Like the tolerance on the laser isn't going to be that good. Like it doesn't really matter. It's red and has been for quite some time. I mean, we're essentially done talking. I mean, so what you do to generate these files, and what I always do to generate these files, is I go to this site. You can bookmark it. You can do whatever. You can Google for Oshpark, KiCad, Gerber, and you'll get to this site. It shows you precisely everything you need. And you generate the files. And you know what the best part about Oshpark is that I really love? Once you generate your Gerbers, you upload them to Oshpark, and then Oshpark will render it for you. So if I go to my projects, and there's a bunch of stuff in here, like, for example, the B-Sides Connecticut 2019 badge, I upload the Gerbers, and Oshpark shows me what it's going to look like. If there's any issues with my Gerbers, if it's generated wrong, if the drill files don't line up, they have automatic scanners to detect that. They'll say, oh, you don't have any bottom silkscreen on your board. It's just a warning. Or, oh, hey, none of your drills line up, by the way. That's an error. But, like, it's not super precise. Like, some, the holes down close, it's all, Anyways, it's something you can upload to Twitter and be like, yeah, look at this thing. Even though, we're not ordering it in purple. So, I mean, obviously another thing that you could do is upload the KiCad 3D model render, because that also looks pretty good, because they actually do have a ray casting engine. So if I, come on. If I do this and get the lighting nice and, get all artistic with it, with my thin boy. And then where is it? We want orthographic projection instead of perspective. And then we render. And your GPU spins up. So the first thing it does is it's casting rays on every location. And then once it finishes, it'll do a finished lighting pass, and it'll get much brighter. The only thing that I don't like about the ray casting is if you ever need to look at the bottom of the board, it's not smart enough to cast the rays out of where you're looking, and you can't move the light. So one side looks real super nice, and the other side looks dark as hell. And, yeah. I mean, there are better ray casters out there, but to be able to do this in like half a second, it looks pretty nice. And it does glitch out a little bit. I mean, like, there's that triangle right there where it's like, what were you doing? And inside this pad here, it's got like bits of copper just hanging there. But, for the most part, if you don't zoom in too close, you don't look too hard, looks pretty nice. What? Oh, the thin boy? I was showing people how you can modify the 3D model in such a way that it would be visible to the human eye. So we have thin boy. Anyways, thanks for coming to my TED Talk. My microphone has been dead for hours. I knew this would go on.